Picture the absolute silence of deep space. No wind, no sound, only the ancient dance of gravity pulling matter through an endless star-scattered void. Here, millions of kilometers from the sun's warming embrace, nothing should be alive. Nothing should be moving. Nothing should be changing. Yet something is. In the cold darkness beyond Mars, a visitor glides through our solar system with the grace of a celestial ghost. Its name is 3I Atlas, the third confirmed interstellar object humanity has ever witnessed. But this traveler is doing something that defies every rule we thought we understood about the cosmos. It's bleeding water into the void, not a gentle seepage, not a slow sublimation that textbooks describe. Atlas is hemorrhaging massive torrents of water vapor, 40 kilograms every second, in a place where ice should remain frozen for eternity. The sunlight here is barely a whisper compared to Earth's blazing noon, yet something inside this ancient wanderer is boiling. The discovery sent ripples through the astronomical community like a stone dropped into still water. For decades, scientists have studied comets with the confidence of familiarity. They knew the rules. They understood the physics. A comet approaches the sun, heats up, releases gas and dust, creates a tail, then retreats back into the cold. Simple, predictable, natural. Atlas shattered that certainty in the most elegant way possible, by simply existing. The object itself appears unremarkable at first glance. A dark, irregular chunk of rock and ice, perhaps a kilometer across, tumbling through space with the patience of geological time. Its surface bears the scars of countless impacts, the weathering of cosmic radiation, the slow erosion of eons spent wandering between the stars. To the naked eye, it would be invisible. To our most powerful telescopes, it appears as nothing more than a faint, moving dot against the star field. But appearances, as Atlas reminds us, can be profoundly deceiving. The first clue emerged from NASA's Neil Gehrels Swift Observatory, a space telescope designed to hunt for the most violent explosions in the universe. Swift's ultraviolet eyes, accustomed to witnessing the death throes of massive stars, detected something far more subtle, yet equally extraordinary. The spectral signature of water, not liquid water, but the ghostly molecular fragments of H2O molecules torn apart by starlight, hydroxyl radicals. O molecules dancing in the vacuum, each one a testimony to water's recent presence. The signature was unmistakable, undeniable, and completely impossible according to conventional wisdom. Dr. Dennis Badowitz, the astronomer who first analyzed the data, described each detected molecule as a message from another planetary system. His words carry a weight that transcends mere scientific observation. If molecules can be messages, then Atlas isn't just a comet. It's a cosmic messenger, carrying news from a world we'll never see, under a sun whose light died before our own star was born. The implications ripple outward like waves in a cosmic pond. If Atlas can release water so far from the sun, what other assumptions about interstellar objects might be wrong? How many other visitors have passed through our system, carrying out their mysterious processes in the darkness, unnoticed and undetected? The mystery deepens when we consider the sheer volume of water being released. 40 kilograms per second might not sound like much in earthly terms, roughly equivalent to a garden hose running at full pressure. But in the context of space, where every molecule must overcome the weak but persistent pull of gravity to escape, this represents an extraordinary expenditure of energy. Something inside Atlas is driving this process. Something active. Something that refuses to remain dormant in the cosmic cold. As Atlas continues its journey through our solar system, it leaves behind more than just a trail of water vapor. It leaves questions that gnaw at the edges of our understanding. Questions that whisper of possibilities we haven't yet learned to imagine. Questions that suggest the universe might be far stranger, far more alive than we ever dared to believe. The comet that shouldn't exist is forcing us to confront a humbling truth. Perhaps it's not the comet that's impossible. Perhaps it's our understanding that's incomplete. Before Atlas became a mystery that would challenge our understanding of physics, it was simply light. A faint, greenish pinprick moving against the star field with purposeful haste. The kind of wandering light that might catch an astronomer's eye during a routine survey. if they happened to be looking in the right direction at the right moment. The discovery came, as many great discoveries do, through the patient accumulation of tiny details. But something about this object's trajectory felt wrong. As more observations accumulated over the following days and weeks, a pattern emerged that made astronomers pause and recalculate. The orbital elements, those mathematical signatures that define how an object moves through space, painted a picture that defied easy categorization. This wasn't a comet from the Oort cloud, that spherical shell of ice and rock that surrounds our solar system like a distant embrace. This wasn't even a visitor from the Kuiper belt, that ring of ancient debris beyond Neptune's orbit. This object was moving too fast, its trajectory too extreme, its orbit too eccentric to belong to our sun's gravitational family. Dr. Robert Warwick, one of the astronomers who had previously discovered Oumuamua, recognized the telltale signs immediately. The hyperbolic orbit, a path that curves once around the sun and then stretches away into interstellar space, never to return. The excess velocity, speed that no amount of gravitational acceleration from our sun could account for. The strange inclination, an angle that suggested this visitor had approached our solar system from below, threading its way up through the plane where the planets orbit like a needle-piercing fabric. By March 2023, the reclassification was official. C2023A3 became 3I Atlas, the third confirmed interstellar object in human history. The 3I designation carries profound weight. It places this object in an exclusive category that barely existed before 2017. Before Oumuamua, we had theories about interstellar visitors. We suspected they must exist. Logic demanded it. The galaxy is vast, filled with billions of star systems, each one occasionally ejecting debris from their gravitational embrace. Some of that debris must inevitably wander between the stars, crossing the dark light years that separate one solar system from another. But suspecting and seeing are different things entirely. Oumuamua opened our eyes to the reality of interstellar space traffic. 2I Borisov confirmed it wasn't a singular event, and now Atlas suggests that these visitors might be more common than we ever imagined, and far more active than we ever expected. The journey that brought Atlas to our doorstep began long before human civilization drew its first breath. Computer models running backward through time suggest this object has been wandering through interstellar space for millions of years. It has drifted past suns whose names we'll never know, through stellar neighborhoods that exist only as points of light in our night sky. Imagine that journey. The slow, patient drift through the cosmic void, where temperatures hover just above absolute zero, and the only light comes from distant stars. For millennia upon millennia, Atlas tumbled through this emptiness, carrying within its frozen body the chemical signature of whatever world gave it birth. Water ice, frozen carbon dioxide, organic molecules, perhaps even the building blocks of life itself, locked in crystalline prisons waiting for the touch of starlight to set them free. The gravitational pull of our sun began influencing Atlas' trajectory long before it entered the realm of the outer planets. Like a cosmic fisherman's net, our star's gravity well bent the visitor's path, drawing it inward through a journey that would take it past Mars, between Earth and Venus, and ultimately around the sun in a graceful parabolic arc. But Atlas wasn't a passive participant in this cosmic dance. Unlike Oumuamua, which remained stubbornly silent throughout its passage, Atlas began to sing, not in sound, but in the language of light and vapor. As it approached the outer solar system, still far beyond the orbit of Mars, something awakened within its ancient structure. The first whispers of activity appeared as a faint coma, a gossamer envelope of gas and dust surrounding the nucleus like morning mist around a mountain peak. This was expected. Comets develop comas as they approach the sun, and their ices begin to sublimate. But what wasn't expected was the timing. Atlas began outgassing while still more than 300 million kilometers from the sun, roughly twice the distance between Earth and Mars. At such distances, solar heating should be negligible. Surface temperatures should hover around 200 degrees Celsius, cold enough to keep water ice as solid as granite. Yet something was driving gas from Atlas's surface with remarkable efficiency. The greenish tint that gave Atlas its distinctive color comes from diatomic carbon, C2 molecules excited by ultraviolet radiation and fluorescing in the green portion of the spectrum. But beneath that familiar comet signature lurked something far more mysterious: the spectral fingerprint of massive water vapor release in a region of space where water should remain permanently frozen. As astronomers around the world turned their instruments toward this unexpected visitor, they began to realize they weren't simply observing another interstellar comet. They were witnessing something that challenged fundamental assumptions about how such objects behave in the cold depths of space. The visitor from another sun had arrived carrying secrets that would force us to question everything we thought we knew about the travelers between the stars. In the silent orbits above Earth, NASA's Neil Gehrels Swift Observatory maintains its patient vigil. Named after a pioneering astronomer who dedicated his life to understanding the most violent events in the cosmos, Swift was designed to detect gamma ray bursts, the explosive death screams of massive stars collapsing into black holes. Its instruments peer across the universe, watching for the brief, brilliant flashes that mark the end of stellar lives and the birth of cosmic monsters. But on this particular day in early 2023, Swift's ultraviolet eyes turned toward something far more subtle. Something that whispered rather than screamed. Something that challenged everything astronomers thought they understood about interstellar visitors. Dr. Dennis Bodowitz received the data transmission with the routine calm of a scientist accustomed to parsing the universe's messages. Swift's ultraviolet optical telescope had been tracking 3I Atlas for several observation periods, building up a spectral portrait of this mysterious visitor. The initial data looked reassuringly normal, the familiar signatures of a comet beginning to awaken as it approached the sun. Then Bodowitz saw the hydroxyl lines. Hydroxyl, OH, is water's molecular ghost. When water molecules encounter ultraviolet radiation, they fracture along predictable lines, splitting into hydrogen and hydroxyl radicals. These OH fragments absorb and emit light at specific wavelengths, creating spectral signatures as distinctive as fingerprints. For astronomers, detecting hydroxyl is equivalent to detecting water's recent presence. But the strength of Atlas's hydroxyl signature made Bodowitz pause and recalculate. The numbers didn't match any conventional model of comet behavior. The intensity suggested water production rates far beyond what solar heating alone could drive at such distances from the sun. 40 kilograms per second. The number seemed to glow on his computer screen with impossible intensity. Atlas was releasing water vapor at a rate of 40 kilograms every second, equivalent to about 88 pounds of water transformed from ice to gas and hurled into the vacuum of space every moment that passed. Over the course of a single day, this represented more than 3 million kilograms of water, enough to fill a small swimming pool, launched into the cosmic void with the persistence of a natural law. The implications were staggering. At Atlas's distance from the sun, roughly 300 million kilometers away, solar flux provides less than 1/9 the energy that reaches Earth's orbit. Surface temperatures on the comet should hover around 180 degrees Celsius, cold enough to freeze carbon dioxide solid. Yet somehow, Atlas was behaving as if it were basking in intense solar radiation, its water ice sublimating with the enthusiasm of summer snow and desert heat. Bodowitz cross-referenced the data with atmospheric models, checking and rechecking his calculations. He consulted databases of previously observed comets, looking for precedents or parallels that might explain what Swift was seeing. He found none. Traditional comet models predict water production rates based on a simple relationship. As distance from the sun decreases, solar heating increases, and sublimation accelerates according to well-established thermodynamic principles. But Atlas was producing water vapor at rates that suggested either unprecedented efficiency in converting solar energy to sublimation, or the presence of an additional energy source entirely. The Swift Observatory's data revealed another puzzling detail. The water production wasn't constant or smoothly varying, it pulsed. Atlas exhibited periodic brightening and dimming, as if its water release came in organized bursts rather than the steady outgassing typically observed in conventional comets. These variations suggested that whatever process was driving the water production was structured, possibly related to the object's rotation or internal dynamics. Each pulse of brightness corresponded to a fresh surge of hydroxyl emission. Thousands of kilograms of water transformed to vapor and expelled into space in organized waves. The precision of these pulses spoke to underlying mechanisms that remained completely mysterious. Dr. Bodowitz found himself confronting data that demanded explanation, but offered few clues about its origin. He had studied comets for decades, watched dozens of these ancient wanderers approach the sun, and release their volatile inventories in predictable patterns. Atlas was following no pattern he recognized. The scientist in him demanded skepticism. Extraordinary claims require extraordinary evidence, and the claim that an interstellar comet could produce massive amounts of water vapor in the cold depths of the outer solar system was certainly extraordinary. But the data was robust, confirmed by multiple observation periods backed by Swift's proven instrumentation. As news of the discovery began to circulate through the astronomical community, it sparked intense debate. Some suggested instrumental error or misinterpretation of the spectral data. Others proposed exotic scenarios involving internal heating mechanisms or unusual composition. But as independent observations confirmed Swift's findings, the astronomical community was forced to confront an uncomfortable truth. Atlas was real. Its water production was real. And neither could be explained by conventional understanding of how interstellar objects should behave. The comet that arrived from another star system had brought with it a mystery that would challenge fundamental assumptions about the nature of matter and energy in the cold depths of space. Each molecule of water vapor streaming from its surface carried a question mark, a challenge to human understanding wrapped in the elegant simplicity of H2O. In the language of molecules escaping into vacuum, Atlas was telling us that the universe still held secrets we had never learned to read. Visualization is the astronomer's greatest tool for comprehending the incomprehensible. When dealing with objects millions of kilometers away, moving at speeds that dwarf human experience, the mind seeks familiar analogies to grasp unfamiliar realities. For 3i Atlas, that analogy became a fire hose. A cosmic fire hose spraying water into the vacuum with relentless, impossible intensity. Picture a garden hose on Earth, connected to municipal water pressure, shooting a steady stream across a suburban lawn. The flow rate might reach 20 or 30 liters per minute under ideal conditions. Now imagine scaling that hose up to cosmic proportions and pointing it into the absolute void of space where every molecule of water must overcome gravitational binding energy to escape into the darkness. Atlas was operating at 40 kilograms per second, roughly equivalent to 2,400 liters per minute. A cosmic fire hose spraying water at nearly 80 times the rate of its earthly counterpart, sustained not by municipal water pressure, but by some mysterious internal process that defied conventional explanation. The visual metaphor became even more striking when astronomers began mapping the spatial distribution of Atlas's water vapor production. Rather than a uniform sublimation from the entire surface, the pattern expected from solar heating alone, the water appeared to be jetting from specific locations on the comet's surface. High-resolution spectroscopic observations revealed distinct plumes of hydroxyl emission, suggesting that Atlas possessed active vents or geysers that focused its water production into organized streams. These jets weren't random or chaotic. They exhibited structure, direction, and remarkable persistence. As Atlas rotated, completing one full rotation approximately every 7 hours, the jets swept through space like cosmic lighthouse beams, their hydroxyl signatures brightening and dimming with clockwork regularity. Dr. Cyrielle Aupetom, who led follow-up observations from the European Southern Observatory, described watching Atlas through her telescope as witnessing something alive. The comet's brightness variations, its structured jets, its rhythmic pulsing of water vapor production, all suggested an object that was actively responding to internal processes rather than passively sublimating under solar influence. But what could drive such activity at distances where sunlight provides barely enough energy to warm a surface by a few degrees above absolute zero? Traditional comet science offers several mechanisms for volatile release. Solar heating sublimation is the most common, direct conversion of surface ice to vapor under the influence of solar radiation. Crystalline phase transitions can release stored energy as amorphous ice transforms to crystalline structures. Radioactive decay of unstable isotopes can provide internal heating over geological timescales. None of these mechanisms could account for Atlas's observed behavior. Solar heating calculations for Atlas's distance from the Sun predict water production rates measured in grams per second, not kilograms. The object would need to be absorbing and converting solar energy with impossible efficiency, far beyond the theoretical limits of black-body radiation physics. Crystalline phase transitions occur primarily when comets first approach the inner solar system, releasing energy stored during their formation billions of years ago. But Atlas had been active far beyond the traditional snow line, where such transitions typically occur, and its production rates showed no signs of the exponential decay expected from finite energy reserves. Radioactive decay provides steady long-term energy output, but the isotopes required to drive Atlas' observed activity would need to be present in concentrations orders of magnitude higher than any previously measured in solar system objects. The comet would essentially need to be a dirty radioactive bomb, which seemed improbable given its apparent structural integrity. As conventional explanations fell short, astronomers began considering more exotic possibilities. Perhaps Atlas contained unusual volatile compounds, substances that sublimate at temperatures far below water ice. Perhaps its internal structure created pressure differences that drove active outgassing through subsurface cavities. Perhaps it harbored chemical reactions powered by cosmic ray bombardment or interstellar medium interactions. Each possibility raised as many questions as it answered. If Atlas contained exotic volatiles, where did they originate? What stellar environment could produce a comet with such unusual chemistry? If internal pressure drove the outgassing, what mechanisms maintained that pressure during millions of years of interstellar wandering? The fire hose metaphor became increasingly apt as astronomers realized they were witnessing sustained, organized water production that seemed to draw from inexhaustible internal reserves. Unlike terrestrial water sources that depend on external pressure or gravity, Atlas appeared to be generating its own driving force, some internal engine that converted unknown energy into the kinetic motion needed to expel massive quantities of water vapor into space. Spectroscopic analysis revealed that the water vapor was emerging at velocities consistent with thermal sublimation, roughly 500 meters per second at the temperatures estimated for Atlas's surface. This suggested that whatever process was driving the water production was creating conditions that mimicked intense solar heating, even in the cold depths where sunlight whispered rather than blazed. The mystery deepened when observers realized that Atlas's water production showed no signs of declining as it moved away from the sun. Conventional comets exhaust their volatile reserves or retreat into dormancy as solar heating diminishes. Atlas continued its fire hose performance with mechanical persistence that suggested vast internal reserves or a fundamentally different energy source. In the cosmic void where nothing should be active, where ice should remain frozen for eternity, Atlas was writing its signature in water vapor with the bold strokes of an artist who had never learned the word impossible. Water is the universe's most eloquent storyteller. Its molecular simplicity, 2 hydrogen atoms bonded to 1 oxygen, belies its profound significance in cosmic chemistry. When astronomers detect water's spectral signature, they're reading a story written in the language of atoms, a narrative that speaks of stellar births, planetary formation, and perhaps even the origins of life itself. The story that Atlas was telling through its water vapor made no sense according to conventional physics. Dr. Dennis Bodowitz, analyzing the Swift Observatory data with the meticulous care of a cosmic translator, found himself confronting molecular evidence that challenged fundamental assumptions about energy and matter in the cold depths of space. The hydroxyl radicals streaming from Atlas carried information encoded in their spectral lines, temperature data, velocity measurements, production rates, that painted a picture of thermodynamic impossibility. Each OH molecule represented a water molecule's death and transformation. Under normal circumstances, this transformation requires energy, specifically the energy needed to break the hydrogen-oxygen bonds that hold H2O together. On Earth, this happens through various processes: evaporation under solar heating, chemical reactions that release thermal energy, or mechanical processes that add kinetic energy to water molecules. In space, the dominant mechanism is photodissociation, ultraviolet radiation from the sun striking water molecules and providing enough energy to fracture them into constituent parts. One photon hits one molecule, breaks specific chemical bonds, and creates hydroxyl radicals that fluoresce at characteristic wavelengths when excited by additional radiation. But the mathematics of photodissociation at Atlas's distance from the sun simply didn't add up. Solar flux at 300 million kilometers provides roughly 1/9 the energy available in Earth's orbit. At such distances, ultraviolet photon density drops to levels where photodissociation should be a rare, sporadic process. Yet Atlas was producing hydroxyl radicals at rates suggesting photodissociation occurring with the efficiency of objects much closer to the sun. The spectral analysis revealed another troubling detail. The hydroxyl emission lines showed Doppler shifts indicating that water vapor was escaping from Atlas at velocities consistent with thermal sublimation at temperatures around 120 degrees Celsius. This might sound cold by terrestrial standards, but it represented surface conditions nearly 60 degrees warmer than solar heating alone could provide at Atlas's location. Dr. Badowitz found himself calculating and recalculating energy budgets, searching for any mechanism that could account for the observed phenomena. Direct solar heating fell short by orders of magnitude. Reflected sunlight from nearby celestial bodies was negligible. Internal radioactive decay would require isotope concentrations that violated everything known about comet composition. The water that was streaming from Atlas in massive quantities simply shouldn't exist in vapor form at the location where Atlas was producing it. Independent observations from ground-based telescopes confirmed the Swift Observatory's findings and added additional layers of mystery. The Very Large Telescope in Chile detected not only hydroxyl, but also the spectral signatures of atomic oxygen, evidence that water molecules were being completely dissociated, not just partially fragmented. This complete molecular breakdown required even more energy than simple hydroxyl production. Radio telescopes detected the microwave emissions of water molecules themselves, confirming that Atlas was indeed producing H2O in gas form, not just the dissociation products that resulted from ultraviolet bombardment. The radio signatures allowed astronomers to measure the total water production rate directly, eliminating any uncertainty about the interpretation of optical and ultraviolet observations. The numbers were undeniable. Atlas was converting approximately 40 kilograms of water ice to vapor every second, sustaining this production rate with remarkable consistency across observation periods spanning several months. The total energy required for this process, accounting for sublimation enthalpy, molecular kinetic energy, and gravitational binding energy, exceeded any plausible internal energy source by factors that made conventional explanations seem absurd. Some astronomers proposed that Atlas might possess an unusually dark surface that absorbed solar radiation with extraordinary efficiency. But even perfect blackbody absorption couldn't account for the observed water production rates. The mathematics of thermodynamics imposed absolute limits that Atlas appeared to violate with casual indifference. Others suggested that the comet might contain trapped carbon monoxide or other highly volatile substances that could sublimate at much lower temperatures than water ice. But spectroscopic analysis showed no evidence of the exotic chemistry required to support such scenarios. Atlas appeared to be composed of fairly ordinary comet materials, water ice, silicate dust, and organic compounds, yet it was behaving in completely extraordinary ways. The philosophical implications began to weigh on researchers studying the object. If Atlas was producing water vapor through unknown mechanisms, what did that say about the completeness of human understanding of basic physics? Were there energy sources or thermodynamic processes that had somehow escaped scientific attention, despite centuries of careful study? Dr. Badowitz, reflecting on the accumulating data, described each molecule of escaping water as carrying a message from another planetary system. But as the evidence mounted, those messages seemed to be written in a language that human science had never learned to read. In the cosmic library where water molecules serve as ancient texts, Atlas was displaying volumes that challenged the fundamental grammar of physics itself. Active surface area is the astronomer's measure of a comet's awakening. Most comets, those ancient remnants of solar system formation, maintain a sleepy existence for most of their orbits. Only a small fraction of their surface, typically 3 to 5%, actively sublimates when exposed to solar radiation. The rest remains dormant, covered by dust and refractory materials that insulate underlying ice from the sun's warming touch. Atlas shattered this expectation with characteristic defiance. Detailed photometric analysis revealed that approximately 8% of Atlas's surface area was actively producing gas and dust, a figure that made astronomers pause and recalculate their measurements. 8% might seem like a modest number, but in the context of comet behavior, it represented unprecedented activity levels that suggested something profound about Atlas's internal structure or energy sources. Dr. Cyrielle Opitom, leading the observational campaign from multiple ground-based telescopes, found herself documenting activity patterns that defied every model of normal comet behavior. Traditional comets awaken gradually as they approach the sun, with active regions expanding slowly as solar heating penetrates deeper into their structure. Atlas displayed vigorous activity from the moment it became detectable, maintaining high production rates across a surface area that suggested either unusual composition or extraordinary energy availability. The 8% figure became even more remarkable when considered in absolute terms. Atlas's estimated nucleus diameter of roughly 1 kilometer suggested a total surface area of approximately 3 square kilometers. 8% of that area, roughly 2,400 square meters, was actively venting material into space with the intensity of industrial-scale sublimation. To visualize this scale of activity, imagine 8 soccer fields worth of ice surface simultaneously sublimating at rates sufficient to launch 40 kilograms of water vapor into space every second. The energy requirements for such widespread intensive sublimation far exceeded anything that solar heating could provide at Atlas's distance from the sun. But the mystery deepened when researchers analyzed the spatial distribution of this active area. High-resolution imaging revealed that Atlas's activity wasn't randomly distributed across its surface. Instead, the outgassing appeared to be concentrated in discrete jets or plumes, organized features that suggested underlying structural controls on volatile release. These jets weren't ephemeral or temporary phenomena. Repeated observations over multiple rotation periods showed that Atlas's active regions maintained consistent orientations and production rates, as if the comet possessed permanent vents or geysers that operated with mechanical regularity. The consistency suggested that whatever process was driving the outgassing was stable, long-lived, and deeply integrated into Atlas's internal architecture. Thermal modeling of Atlas's surface conditions revealed another puzzling aspect of the 8% mystery. Even if solar heating could somehow drive sublimation across such a large surface area, the resulting cooling effects should create temperature gradients that would shut down activity in all but the most favorably oriented regions. Sublimation is an endothermic process. It absorbs heat and cools the surrounding material. Sustained sublimation across 8% of a comet's surface should rapidly freeze the active regions into dormancy. Yet Atlas maintained its extraordinary activity levels with the persistence of a natural law. Spectroscopic analysis of the outgassing regions revealed additional complexity. The jets weren't producing uniform mixtures of water vapor and dust. Different active regions showed distinct spectral signatures, suggesting variations in subsurface composition or processing mechanisms. Some jets were water-rich, others showed enhanced dust content, and a few displayed spectral lines indicating the presence of more exotic volatile compounds. This chemical diversity across Atlas's active regions hinted at internal heterogeneity that exceeded anything observed in conventional solar system comets. Most comets show relatively uniform composition across their surface, reflecting their formation from well-mixed primordial materials. Atlas appeared to harbor distinct chemical domains, each with its own volatile inventory and outgassing characteristics. The implications were staggering. If Atlas had formed in an interstellar environment with access to diverse chemical inputs, it might represent a fundamentally different class of object than the comets familiar from our own solar system. Its 8% activity level might be normal for interstellar comets, suggesting that our understanding of comet behavior was based on a limited sample of locally formed objects. Alternatively, Atlas might be experiencing internal processes that were actively creating new volatile materials or mobilizing previously frozen reserves. Some theoretical models suggested that cosmic ray bombardment during millions of years of interstellar wandering could create unusual chemical species that would become active when exposed to even minimal solar heating. Dr. Opatom's team conducted rotation phase analysis to understand how Atlas's activity varied with its orientation relative to the Sun. Most comets show predictable brightness and outgassing variations as different regions of their surface experience day-night cycles. Atlas showed variations, but they were far more complex than simple solar illumination could explain. The active regions seemed to pulse with organized rhythms that suggested internal dynamics rather than external forcing. Some jets would intensify while others dimmed, creating interference patterns in the overall brightness that spoke to underlying processes that remained completely mysterious. As the observational data accumulated, the 8% mystery began to symbolize something larger than unusual activity levels. It represented a fundamental challenge to the assumption that interstellar objects would behave like their solar system cousins. Atlas was demonstrating that the universe might harbor entire classes of objects that operated according to principles human science had never encountered. In the cosmic census of active surfaces, Atlas had announced itself as something entirely new, an object where awakening wasn't gradual or predictable, but immediate, intensive, and sustained by energy sources that remained tantalizingly beyond comprehension. Language exists wherever patterns carry meaning. In the realm of molecular astronomy, every spectral line represents a word, every emission feature a sentence, every complex spectrum an entire narrative written in the fundamental vocabulary of atoms and energy. When Dr. Dennis Bodowitz described each molecule of water vapor streaming from Atlas as a message from another planetary system, he was acknowledging a profound truth about the nature of scientific observation. We are cosmic archaeologists, reading the history of distant worlds and the chemical signatures of wandering debris. The messages that Atlas was broadcasting in its water vapor carried information encoded at multiple levels. At the most basic level, the mere presence of water molecules told a story about the comet's origins. Water forms under specific conditions of temperature, pressure, and chemical availability. Its existence within Atlas suggested formation in an environment where hydrogen and oxygen could combine and remain stable, likely within the circumstellar disk of a star system where planets might also form. But the isotopic signatures hidden within Atlas's water vapor told deeper stories. Different star systems produce water with subtly different ratios of hydrogen isotopes, regular hydrogen versus deuterium, the heavy isotope that carries an extra neutron. These ratios serve as stellar fingerprints, unique signatures that identify the specific stellar environment where water formation occurred. Early spectroscopic analysis of Atlas's water vapor revealed deuterium to hydrogen ratios that differed subtly but measurably from solar system values. The differences were small, a few parts per million, but they carried enormous significance. Atlas's water had formed around a different star, under slightly different conditions, in a stellar environment with its own unique chemical history. The water molecules streaming from Atlas had witnessed the birth of planets around another sun. They had condensed from stellar nebulae accreted into planetesimals, survived gravitational disruptions that ejected their host object from its birth system, and wandered through interstellar space for millions of years before arriving in our solar system to tell their story through the language of spectral lines. Each molecule was indeed a message, a chemical telegraph from a world humanity would never visit, carrying news of stellar processes that occurred before our own sun ignited nuclear fusion in its core. Dr. Bodowitz and his colleagues found themselves in the role of cosmic translators, parsing molecular messages that had traveled light years through space and millions of years through time to reach their instruments. The translation process required extraordinary precision. Water vapor signatures could be contaminated by terrestrial atmospheric interference, confused with other molecular species, or misinterpreted due to temperature and velocity effects. But as the data accumulated from multiple observation periods and instruments, the messages became clearer. Atlas wasn't just carrying water. It was carrying a complex chemical library that preserved information about interstellar chemistry, stellar nucleosynthesis, and planetary formation processes that had occurred in another star system. Trace amounts of organic molecules detected in Atlas's spectrum told additional stories. Simple carbon compounds, the building blocks of biochemistry, were present in ratios that suggested formation through stellar chemistry rather than biological processes. But their very existence demonstrated that the interstellar medium could preserve complex chemistry across vast distances and timescales. The velocity distribution of escaping water molecules carried its own narrative. Spectroscopic analysis revealed that different water molecules were escaping from Atlas at different speeds, creating a complex Doppler signature that mapped the dynamics of the sublimation process. Some molecules were moving slowly, suggesting gentle sublimation from surface ice. Others were moving at high speeds, indicating explosive release from subsurface regions or chemically driven processes. This velocity dispersion painted a picture of internal complexity that exceeded anything expected from simple solar heating. Atlas appeared to be a stratified object with multiple volatile reservoirs, each operating under different physical conditions and contributing to the overall water vapor message with its own distinctive signature. The temporal variations in Atlas's water vapor production added another layer of meaning to the molecular messages. Rather than steady sublimation, Atlas exhibited periodic bursts of enhanced activity that suggested underlying processes with their own intrinsic timescales. These pulsations might reflect internal heating cycles, structural changes within the comet, or chemical reactions that proceeded according to their own kinetic laws. Dr. Budowitz began to interpret these temporal variations as a form of cosmic Morse code, patterns of activity that might encode information about Atlas's internal structure, energy sources, or chemical evolution. The challenge lay in developing the theoretical framework needed to decode these patterns and extract their hidden meanings. As the observational campaign continued, it became clear that Atlas was broadcasting far more information than any single research group could analyze. The molecular messages streaming from its surface carried data about interstellar chemistry, planetary formation, stellar nucleosynthesis, and perhaps even the distribution of organic molecules throughout the galaxy. Each spectral line represented a library volume, each emission feature a chapter in the story of cosmic chemistry. Atlas had arrived in our solar system carrying the largest collection of interstellar information ever available for detailed study, and it was sharing that information freely with any astronomer patient enough to listen to its molecular whispers. In the universal language of chemistry, written in spectral lines and molecular signatures, Atlas was telling humanity stories about worlds we would never see, processes we could barely imagine, and possibilities that stretch the boundaries of our understanding of how the universe creates and preserves complexity across the vast scales of space and time. The messages were there, encoded in every molecule of escaping vapor. The challenge was learning to read them with sufficient sophistication to appreciate the profound narratives they contained about the cosmos beyond our solar system. The mathematics of celestial mechanics is humanity's most precise form of time travel. Through careful observation of an object's current position and velocity, astronomers can calculate backward through the equations of orbital dynamics to reconstruct journeys that span millions of years and billions of kilometers. For 3I Atlas, this mathematical archaeology revealed a path through space so extraordinary that it reads like science fiction written in the language of gravitational physics. Dr. Marco Micheli, a specialist in orbit determination at the European Space Agency, led the painstaking effort to trace Atlas's trajectory backward through time. Using observations from multiple telescopes spanning several months, his team constructed a mathematical portrait of the comet's motion with unprecedented precision. Each additional observation refined the orbital elements, reducing uncertainty and extending the reliability of retroactive calculations deeper into the past. The process began with Atlas's current hyperbolic orbit, a graceful parabolic curve that brought the comet from the depths of interstellar space, around the Sun, and back toward the cosmic void. But hyperbolic orbits are deceptive in their simplicity. What appears as a smooth curve in space represents the cumulative effect of gravitational influences from every massive object in the solar system, from the Sun's dominant pull to the subtle perturbations of distant planets. Unwinding these influences required computational power that would have been unimaginable just decades ago. Micheli's team employed sophisticated numerical integration techniques, accounting for the gravitational effects of all major planets, the largest asteroids, and even the relativistic corrections that Einstein's general relativity demands for precise orbit calculations. As the mathematical time machine carried Atlas's trajectory backward through the years, a remarkable story emerged. The comet's path led not just out of the solar system, but toward a specific region of the galaxy, where stellar dynamics and galactic rotation had carried it through neighborhoods rich with stellar formation and planetary evolution. 50,000 years ago, Atlas was already an ancient wanderer, drifting through the space between Vega and Altair with the patience of geological time. Its velocity then was roughly 26 kilometers per second relative to the Sun, fast enough to cross the distance between Earth and Moon in just 14 hours, yet representing merely a gentle drift on galactic scales. The trajectory calculations revealed that Atlas had approached our solar system from a direction roughly 30 degrees below the ecliptic plane, the imaginary disk where Earth and the other planets orbit. This angle of approach suggested that the comet's journey had carried it through regions of the galaxy with different stellar densities and chemical environments than our own solar system's neighborhood. A million years before its arrival, Atlas was drifting through the space near the constellation Lyra, passing within a few light years of young, massive stars whose intense radiation fields would have bombarded its surface with cosmic rays and hard ultraviolet photons. This exposure to extreme stellar environments might have altered Atlas' surface chemistry in ways that could explain its unusual activity patterns. The mathematical trail led even further into the past, toward a point roughly 5 million years ago, when Atlas's trajectory became increasingly uncertain. The cumulative effects of gravitational perturbations from passing stars, encounters with interstellar gas clouds, and the galaxy's own differential rotation eventually overwhelmed the precision of retroactive calculations. Beyond that temporal horizon, Atlas's specific origin remained shrouded in mathematical uncertainty. But even without knowing its exact birthplace, the trajectory analysis revealed profound insights about Atlas's cosmic journey. The comet had spent millions of years wandering through regions of the galaxy, with access to chemical environments far more diverse than our own solar system. It had drifted past stellar nurseries where new stars were igniting nuclear fusion, through the aftermath of supernova explosions that scattered heavy elements across interstellar space, and possibly even through the debris fields of other planetary systems. Each environment would have left its mark on Atlas's composition and structure. Cosmic ray bombardment could have created exotic isotopes and unusual chemical compounds. Exposure to varying stellar radiation fields might have processed its surface materials in ways that created the unusual volatile inventories now being observed. Gravitational encounters with other interstellar objects could have altered its internal structure, or triggered processes that remained active even after millions of years. The trajectory analysis also revealed the elegance of Atlas's final approach to our solar system. Rather than a chaotic plunge through the planetary orbits, the comet followed a path of extraordinary grace, approaching from below the ecliptic plane, threading between the outer planets without significant gravitational disturbance and achieving a perihelion distance that brought it close enough to the Sun for detailed observation without risking destruction from excessive heating. Dr. Micheli described this approach as cosmically choreographed, a path so precisely tuned for scientific observation that it seemed almost intentional. The comet's timing, trajectory, and activity level combined to create optimal conditions for studying an interstellar visitor with unprecedented detail. As Atlas continues its journey away from the Sun, trajectory calculations predict its future path with similar precision. The comet will escape our solar system's gravitational influence within the next few thousand years, returning to interstellar space with a velocity slightly increased by its gravitational interaction with the Sun. Its next destination lies in the direction of the constellation Perseus, where it will wander for another million years before gravitational influences from distant stars begin to significantly alter its path. The mathematical portrait of Atlas's journey through space and time reveals it as more than just a comet. It is a cosmic time capsule, a wandering museum that has preserved samples of interstellar chemistry across millions of years and billions of kilometers of travel. Its arrival in our solar system represents a convergence of circumstances so improbable that it borders on the miraculous. In the precise language of celestial mechanics, Atlas's trajectory tells the story of a universe where matter and energy flow freely between star systems, where the chemical products of stellar evolution become the building blocks for new worlds, and where ancient wanderers carry messages across distances so vast that their journeys span the rise and fall of entire civilizations. October 2017 marked a watershed moment in humanity's understanding of the cosmos. Dr. Robert Warwick, studying routine survey images from the Panoramic Survey Telescope and Rapid Response System in Hawaii, noticed something that would forever change our perspective on interstellar space. A faint object moving too quickly and in the wrong direction to belong to our solar system is gravitational family. Humanity is first confirmed visitor from the stars, Wanini Oumuamua, named with the Hawaiian word for scout or messenger, arrived carrying mysteries that continue to perplex astronomers today. Its discovery opened a new chapter in astronomy, proving that interstellar space wasn't empty, but populated with wanderers carrying chemical and physical information from other star systems. But Oumuamua was a reluctant messenger, guarding its secrets with enigmatic silence. The parallels between Oumuamua and Atlas are profound, yet their differences illuminate the extraordinary diversity that appears to characterize interstellar objects. Both follow hyperbolic trajectories that mark them as genuine visitors from other star systems. Both arrived from directions and with velocities that rule out solar system origins. Both challenged fundamental assumptions about how such objects should behave in the cold depths of space. But where Oumuamua whispered, Atlas shouts. Oumuamua remained spectroscopically silent throughout its passage through the inner solar system. No detectable outgassing, no visible coma, no dust tail or ion emissions. It presented the appearance of a completely inert object, a dark, tumbling fragment of interstellar debris that offered few clues about its composition or origin. Yet, Oumuamua exhibited one behavior that defied easy explanation: non-gravitational acceleration. As it receded from the sun, the object moved slightly faster than gravitational dynamics alone could account for. The acceleration was small, barely detectable against the precision limits of orbital determination, but it was real and consistent across multiple observation periods. For conventional comets, such acceleration would be easily explained by outgassing. As volatile materials sublimate and escape from a comet's surface, they create a weak but measurable rocket effect that can alter the object's trajectory. But Oumuamua showed no signs of the outgassing that would be required to produce its observed acceleration. This paradox led to intense scientific debate. Some astronomers proposed that Oumuamua was composed of extremely pure water ice that sublimated without creating detectable vapor signatures. Others suggested exotic scenarios involving hydrogen outgassing or unusual thermal properties. Dr. Avi Loeb, the controversial Harvard astrophysicist, even proposed that Oumuamua might be an artificial object, a solar sail or probe created by extraterrestrial intelligence. Atlas arrived 6 years later as if responding directly to the mysteries that Oumuamua had raised. Where Oumuamua was silent, Atlas was spectacularly active. Where Oumuamua hid its composition behind reflective silence, Atlas broadcast its chemical inventory through massive water vapor production. Where Oumuamua accelerated mysteriously without visible cause, Atlas demonstrated that interstellar objects could indeed exhibit extraordinary activity levels when conditions permitted. The contrast suggests that interstellar objects might span a vast spectrum of compositions, activity levels, and behaviors. Oumuamua might represent one extreme: objects composed primarily of refractory materials that remain essentially inert during passage through the inner solar system. Atlas might represent another extreme: objects rich in volatile materials that become spectacularly active even at large distances from the sun. Between these extremes might lie a continuum of interstellar visitors with intermediate properties. Some might activate only when very close to the sun. Others might exhibit episodic activity triggered by internal processes rather than solar heating. Still others might be composite objects with both active and inert components, creating complex behavior patterns that defy simple categorization. The spectroscopic richness of Atlas provided answers to some questions that Oumuamua's silence had left unresolved. The detection of water vapor, hydroxyl radicals, and trace organic compounds confirmed that at least some interstellar objects carry complex chemical inventories preserved from their formation environments. This supported theories that interstellar wanderers could serve as vectors for chemical exchange between star systems, carrying the products of stellar nucleosynthesis and planetary formation across the galaxy. But Atlas also deepened some of the mysteries that Oumuamua had introduced. If interstellar space contained objects as active as Atlas, why was Oumuamua so different? Were they products of fundamentally different formation processes, or did they represent different evolutionary stages of similar objects? The temporal gap between the two discoveries, roughly 6 years, suggested that interstellar visitors might be more common than previously suspected. If two objects could be detected within such a short period, statistical models implied that dozens or hundreds of similar objects might pass through the solar system undetected during longer timescales. Dr. Warwick, who had discovered both Oumuamua and initially observed Atlas, found himself in the unique position of having detected two of humanity's first 3 confirmed interstellar visitors. He described the experience as watching the universe reveal one of its fundamental properties, that matter flows freely between star systems, carrying information about cosmic processes we're only beginning to understand. The relationship between Oumuamua and Atlas also highlighted the importance of observational capability in determining what humanity could learn from interstellar visitors. Oumuamua was detected late in its passage through the solar system, allowing only limited observation time before it faded beyond detection limits. Atlas was identified earlier in its approach, enabling extended observational campaigns that revealed its extraordinary water vapor production. Future interstellar visitors might be detected even earlier, possibly while still in the outer solar system, where their behavior could be studied across a wider range of solar distances and environmental conditions. Each visitor would add to humanity's growing database of interstellar object properties, gradually revealing the chemical and physical diversity that characterizes matter flowing between the stars. In the cosmic conversation between interstellar visitors, Oumuamua posed questions through its enigmatic silence. Atlas provided some answers through its spectacular activity. But both objects suggested that the universe was beginning to share secrets about the processes that connect star systems across the galaxy. Secrets encoded in the chemical signatures and physical behaviors of ancient wanderers, carrying messages from worlds humanity would never directly observe. The echoes between these two remarkable objects promised that future interstellar visitors would continue revealing new aspects of cosmic chemistry, stellar evolution, and planetary formation processes that operate on scales far larger than our own solar system. Between the enigmatic silence of Oumuamua and the spectacular water vapor symphony of Atlas lies Tuai Borisov, the interstellar comet that served as humanity's first clear bridge between familiar and alien. Discovered in August 2019 by amateur astronomer Gennady Borisov using a homemade telescope, this visitor from the depths of space arrived carrying a chemical signature that was both reassuringly familiar and mysteriously exotic. Borisov appeared to behave like a conventional comet in many respects. It developed a visible coma as it approached the sun. It displayed the characteristic greenish tint of diatomic carbon molecules excited by solar radiation. It outgassed steadily as solar heating warmed its surface, creating a dust tail that stretched gracefully behind its nucleus like a cosmic banner announcing its passage through the inner solar system. But beneath this familiar appearance, Borisov harbored chemical secrets that revealed the profound differences between objects formed in our solar system and visitors from other stellar environments. Spectroscopic analysis of Borisov's coma revealed unusually high concentrations of carbon monoxide, CO molecules that sublimate at much lower temperatures than water ice. While solar system comets typically contain carbon monoxide in modest amounts, Borisov's inventory was remarkable, both for its abundance and its accessibility. The CO was sublimating vigorously at distances where solar system comets would remain largely dormant. Dr. Denis Badowitz, who would later analyze Atlas's extraordinary water vapor production, found himself puzzling over Borisov's carbon monoxide signatures with similar intensity. The abundance of CO suggested formation in a much colder environment than typically characterizes solar system comet formation regions. Borisov had apparently formed in the outer reaches of another star system, where temperatures were low enough to trap and preserve carbon monoxide in concentrations that seemed exotic by local standards. The discovery established Borisov as humanity's first clear example of a normal interstellar comet, an object that exhibited familiar comet behaviors while carrying chemical signatures that marked it as definitively alien. Unlike Oumuamua's mysterious silence or Atlas's spectacular anomalies, Borisov provided a baseline for understanding how interstellar comets might typically behave when they encountered solar heating. But Borisov's normalcy was itself remarkable. The fact that an object formed around another star subjected to different stellar radiation fields and chemical environments for millions of years could arrive in our solar system and behave recognizably like a comet suggested underlying universality in the processes that create and preserve volatile-rich objects. The carbon monoxide that streamed from Borisov's nucleus told stories about stellar chemistry and planetary formation in other star systems. CO forms through specific reactions involving carbon and oxygen under conditions that depend on temperature, pressure, and the availability of other chemical species. Its abundance in Borisov suggested formation in an environment where these conditions differed systematically from those that characterized our own solar system's early history. Some theoretical models propose that Borisov had formed in the outer regions of a stellar system with a more massive central star. Higher stellar masses create larger circumstellar disks with extended cold zones where carbon monoxide can condense and remain stable. Such environments might preferentially produce comets with exotic volatile inventories compared to our own Sun's more modest disk. Other models suggested that Borisov's chemistry reflected formation during a different epoch of galactic chemical evolution. Stars forming billions of years ago had access to different ratios of heavy elements, potentially creating planetary systems with systematically different chemical signatures. Borisov might be carrying samples of interstellar chemistry from an era when the galaxy itself was younger and chemically distinct. The dust composition revealed through polarimetric analysis of Borisov's tail provided additional clues about its formation environment. The silicate particles streaming from its nucleus showed spectral signatures that differed subtly but measurably from solar system comet dust. These differences suggested processing by stellar radiation fields with different spectral characteristics or formation from dust grains with access to unusual chemical inputs. Dr. Stefano Bagnulo, leading the polarimetric studies of Borisov's dust tail, described the particles as cosmic fossils, preserved samples of the interstellar dust from which Borisov had originally accreted. Each grain carried information about stellar nucleosynthesis processes, supernova explosions, and chemical evolution that had occurred in another region of the galaxy. Borisov's relatively conventional behavior also provided crucial calibration for understanding the more extreme properties exhibited by Atlas. If Borisov represented typical interstellar comet behavior, then Atlas's extraordinary water vapor production became even more remarkable by comparison. The spectrum of interstellar visitor behaviors was apparently much broader than early theories had predicted. The observational campaign that followed Borisov through its passage around the Sun revealed temporal variations that hinted at internal structure, more complex than simple homogeneous composition. The carbon monoxide outgassing showed periodic variations that suggested either rotational effects exposing different surface compositions or internal processes that regulated volatile release through mechanisms not yet understood. Near perihelion, Borisov underwent what appeared to be a fragmentation event, a sudden brightening followed by the appearance of multiple components in high-resolution imaging. This behavior paralleled the fragmentation observed in some solar system comets, but added questions about whether interstellar objects might be more structurally fragile due to their extended exposure to cosmic ray bombardment and thermal cycling during millions of years of interstellar travel. The fragmentation provided an unprecedented opportunity to study Borisov's internal composition directly. Fresh surfaces exposed by the splitting event revealed chemical signatures that had been hidden beneath protective surface layers. These interior compositions showed even higher carbon monoxide concentrations than the surface materials, suggesting that Borisov was stratified with the most exotic chemistry preserved in its core. As Borisov faded from view during its departure from the solar system, it left behind a wealth of data that established the foundation for interpreting future interstellar visitors. Its chemical signatures, behavioral patterns, and structural properties created a template for recognizing and understanding interstellar comets that would arrive carrying different but related messages from other star systems. In the growing catalog of interstellar visitors, Borisov served as the essential bridge between the mysterious and the familiar, an object alien enough to reveal the diversity of cosmic chemistry, yet familiar enough to demonstrate the universal processes that create volatile, rich wanderers throughout the galaxy. When Atlas arrived with its spectacular water vapor production, astronomers had Borisov's carbon monoxide signatures as a reference point for understanding how interstellar objects could carry exotic chemical inventories while still behaving according to recognizable physical principles. The bridge between worlds that Borisov provided made Atlas's anomalies even more intriguing by establishing what normal, interstellar comet behavior might actually entail. In the cold orbit of Mars, 200 million kilometers from the Sun, mechanical eyes maintained their patient vigil over the red planet's thin atmosphere and rusty landscape. The European Space Agency's trace gas orbiter, designed to hunt for methane and other trace gases that might betray signs of Martian life, turned its sophisticated cameras toward an unexpected target that had wandered into its field of view. 3i Atlas, glowing with its mysterious water vapor aura, drifted past Mars like a cosmic ghost ship sailing through the rust-colored void. The images captured by the trace gas orbiter's CAS's camera system were hauntingly beautiful in their stark simplicity. Against the star-studded blackness of space, Atlas appeared as a gossamer specter, its nucleus too small and distant to resolve as anything more than a point of light, but its coma visible as a faint, ethereal envelope that caught and scattered sunlight with the delicate luminescence of aurora. From Mars's perspective, Atlas looked like a green star that had broken free from the celestial sphere and begun to wander. The characteristic color came from excited carbon molecules in the comet's coma, fluorescing under ultraviolet radiation with the emerald glow that has marked comets as harbingers and portents throughout human history. But this green star was different from any that had graced Martian skies before. It was a visitor from another sun, carrying water vapor into space through processes that defied conventional understanding. Dr. Nicholas Thomas, principal investigator for the CAS's imaging system, found himself documenting an event of unprecedented scientific and philosophical significance. For the first time in the history of either planet, Mars was serving as an observing platform for studying an interstellar visitor. The red planet, which had once harbored oceans that might have teemed with life, was witnessing the passage of an object that carried water from another world entirely. The irony was profound and poetic. Mars, which had lost its own water to space over billions of years, watched as Atlas sprayed water vapor into the void with the extravagance of a cosmic fountain. The planet that might once have been blue and wet observed a green wanderer that refused to keep its water locked in ice, despite the killing cold of interplanetary space. The images revealed details about Atlas's coma structure that were invisible from Earth-based observations. The low-resolution perspective from Mars orbit eliminated atmospheric interference and provided viewing angles that revealed asymmetries in the comet's vapor production. Rather than a uniform spherical envelope, Atlas's coma showed directional features, jets and plumes that created a distinctly asymmetric brightness distribution. These structural details supported the emerging picture of Atlas as an object with highly localized active regions rather than uniform surface sublimation. The coma asymmetries aligned with theoretical models suggesting that water vapor was being produced by specific vents or geysers that operated with their own internal dynamics rather than simple response to solar heating. The Martian perspective also provided crucial data for understanding Atlas's total water vapor production rate. By measuring the overall brightness and spatial extent of the coma from a different viewing angle, astronomers could triangulate the three-dimensional structure of the vapor envelope and refine their estimates of how much water Atlas was releasing into space. The numbers remained staggering from any observational perspective. Whether viewed from Earth from Mars orbit or from space-based telescopes. Atlas consistently demonstrated water vapor production rates that exceeded theoretical predictions by orders of magnitude. As the trace gas orbiter continued tracking Atlas across multiple observation periods, the images revealed temporal variations that added new layers to the mystery. The coma brightness fluctuated with periodicities that suggested rotational effects, but the variations were far more complex than simple day-night cycles on the comet's surface. Some brightness changes occurred on timescales of hours, possibly reflecting Atlas's rotation period. Others varied over days or weeks, suggesting longer-term processes that might involve changes in internal structure or activation of different volatile reservoirs. The most puzzling variations were rapid brightening events that lasted only minutes, brief flares that suggested explosive release of water vapor through processes that remained completely mysterious. Dr. Thomas described watching these rapid variations as observing a cosmic engine with its own internal rhythm. The precision timing of some brightness fluctuations suggested that whatever processes were driving Atlas water vapor production were highly organized rather than random or chaotic. The Martian observations also captured Atlas during a period when it was simultaneously being studied by the Swift Observatory, ground-based telescopes, and other space-based instruments. This coordinated observational campaign created an unprecedented multi-perspective view of an interstellar object's behavior, revealing details that no single observing platform could have detected independently. The data fusion revealed that Atlas's water vapor production varied not just with time but also with viewing angle. Different perspectives showed different aspects of the comet's activity, confirming that the outgassing was highly directional rather than isotropic. Some jets appeared to be oriented preferentially toward or away from the Sun, while others seemed to follow the comet's rotational axis or other internal structural alignments. As Atlas continued its journey beyond Mars' orbit, the trace gas orbiter's cameras captured its gradual fading with the melancholy beauty of a farewell. The green glow that had marked the comet's presence slowly dimmed as it receded into the outer solar system, its water vapor production continuing, but becoming increasingly difficult to detect against the growing distance. The final images showed Atlas as a fading point of light, its mysterious coma barely visible against the starfield. But even in its diminished state, the comet continued to challenge observers with persistent activity that should have ceased once solar heating became negligible. From Mars' orbit, the ancient red planet had served as humanity's most distant observation post for studying an interstellar visitor. The images captured by the trace gas orbiter would stand as historical documents, the first photographs of an active interstellar comet taken from another world, marking a new era in humanity's ability to study the chemical and physical processes that connect star systems across the galaxy. In the cosmic theater where Mars served as witness, Atlas had performed its water vapor symphony before an audience that spanned two worlds and multiple star systems, a reminder that the universe operates on scales and through processes that continue to exceed human imagination, even as our technological capabilities expand to meet the challenge of understanding them. In the quiet corridors of Harvard University's Department of Astronomy, where equations describe the behavior of black holes and stellar evolution proceeds with mathematical precision, Professor Avi Loeb has made a career of asking uncomfortable questions. When the rest of the astronomical community seeks natural explanations for cosmic phenomena, Loeb systematically explores the possibility that some observations might require artificial explanations, that the universe might harbor evidence of intelligence operating on scales we're only beginning to comprehend. His controversial interpretation of Oumuamua as possibly artificial had already established him as astronomy's most prominent provocateur. When Atlas arrived with its spectacular water vapor production, Loeb saw an opportunity to push the boundaries of scientific speculation even further into territory that most astronomers preferred to avoid. "We should consider all possibilities," Loeb stated during a Harvard colloquium in early 2023, his calm voice carrying the weight of careful reasoning rather than sensational claims. If an object is doing something that natural processes cannot easily explain, then artificial processes deserve consideration as working hypotheses. For Atlas, Loeb's artificial hypothesis took several forms, each more challenging to conventional thinking than the last. The simplest version suggested that Atlas might be a probe, an artificial object designed by extraterrestrial intelligence to study stellar systems by passing through them and collecting data. Its water vapor production might represent not sublimation, but active systems designed to create observational signatures that would attract attention from any technological civilizations in the target system. This interpretation reframed Atlas's mysterious energy source as potentially technological rather than thermodynamic. Instead of asking what natural process could drive massive water vapor production in the cold depths of space, Loeb suggested asking what artificial process might be designed to produce exactly such signatures. The distinction was subtle but profound. It shifted the investigation from seeking unknown physics to considering known technology operating at scales beyond current human capability. A more speculative version of Loeb's hypothesis proposed that Atlas might be a seed, an artificial object designed to distribute materials that could influence planetary formation in target star systems. Its water vapor production might represent the gradual dispersal of carefully chosen chemical materials intended to alter the composition of our solar system's outer regions. This seeding hypothesis drew inspiration from concepts in directed panspermia, the theoretical possibility that advanced civilizations might deliberately spread the chemical foundations for life throughout the galaxy. Atlas's exceptional water production rates and unusual chemical signatures might indicate a systematic attempt to introduce alien biochemistry into our solar system's environment. The most ambitious version of Loeb's artificial hypothesis suggested that Atlas might be engaged in active terraforming, attempting to alter our solar system's chemical environment in ways that would make it more suitable for specific forms of life or technology. The massive scale of its water vapor production, if sustained over long periods, could theoretically alter the chemical composition of the interplanetary medium throughout the outer solar system. Loeb's provocation served a crucial function in the scientific discourse surrounding Atlas, even though most astronomers remained skeptical of artificial explanations. By systematically articulating what artificial intelligence might look like if deployed on interstellar scales, he forced the scientific community to be more precise about what natural processes could and could not explain. His analysis highlighted the energy budget problems that plagued natural explanations for Atlas's behavior. If solar heating could not account for the observed water vapor production, and if known internal energy sources were insufficient, then the scientific community needed to either discover new physics or consider alternative explanations that operated outside conventional assumptions about how natural objects behave. Dr. Dennis Bodowitz, while remaining skeptical of artificial hypotheses, acknowledged that Loeb's provocations served valuable scientific purposes. Extraordinary claims require extraordinary evidence, Bodowitz noted, but extraordinary observations also require extraordinary explanations. If our best natural models cannot account for what we're seeing, then we need to expand our theoretical framework until they can. Loeb's approach to Atlas exemplified his broader philosophy about scientific conservatism versus scientific progress. He argued that the astronomical community's reflexive preference for natural explanations, while generally justified by historical success, might blind researchers to genuinely artificial phenomena if they occurred. The universe might harbor technological activities on scales that dwarf human capabilities, but conventional scientific methodology might systematically overlook such activities by assuming they cannot exist. The artificial hypothesis also raised profound questions about the nature of intelligence and technology on cosmic scales. If Atlas were indeed artificial, what kind of civilization would have the capability to launch objects across interstellar distances with precision targeting and sustained technological functionality? What purposes might drive such massive engineering projects? How might human civilization eventually develop similar capabilities? These questions extended far beyond Atlas itself to encompass fundamental issues about the prevalence and detectability of intelligence throughout the galaxy. If artificial objects were wandering between star systems with sufficient frequency to be occasionally detected by human surveys, then the galaxy might be far more populated with technological civilizations than traditional estimates suggested. Loeb's analysis also explored the observational signatures that might distinguish artificial from natural interstellar objects. Artificial objects might exhibit greater structural complexity, more precisely controlled trajectories, communication attempts, or responses to observation that natural objects would not display. Atlas's organized water vapor jets and periodic activity variations might represent such artificial signatures, though natural explanations remained plausible. The broader scientific community remained deeply skeptical of artificial explanations for Atlas, preferring to exhaust natural possibilities before considering technological alternatives. But Loeb's systematic articulation of artificial hypotheses served to sharpen the focus on exactly which natural processes needed to be discovered or better understood to account for Atlas' extraordinary behavior. Whether artificial or natural, Atlas was forcing astronomy to confront the limitations of current theoretical frameworks and observational capabilities. Loeb's provocations ensured that this confrontation would be comprehensive, considering possibilities that conventional scientific conservatism might otherwise overlook. In the cosmic conversation about intelligence and technology on galactic scales, Atlas had arrived as either a natural phenomenon that challenged human understanding of physics or an artificial phenomenon that challenged human understanding of intelligence itself. Loeb's role was to ensure that both possibilities received the systematic analysis they deserved, regardless of their conventional plausibility. His provocations reminded the scientific community that the universe might be far stranger and more populated than current theories suggested, and that distinguishing between the impossible and the merely unprecedented required intellectual courage as well as observational precision. In the grand theater of stellar evolution, where gas giants form from swirling disks of dust and ice, a remarkable process unfolds over millions of years. Tiny particles of cosmic debris gradually accumulate into larger aggregates, building through gravitational attraction and electromagnetic forces until they reach the critical mass needed to sweep up surrounding material and grow into planets. But this process faces a notorious bottleneck known as the meter barrier, a size range where growing objects become trapped between competing physical forces. Dr. Sean Raymond, a planetary formation theorist at the Laboratoire d'Astrophysique de Bordeaux, has spent decades studying this cosmic construction process and the obstacles that can halt it. His work on how planets overcome the meter barrier led him to a startling realization when Atlas arrived in our solar system. Interstellar objects like this mysterious water-spewing comet might serve as cosmic seeds that accelerate planetary formation around other stars. The planet seed hypothesis emerges from understanding the physics of how matter aggregates in circumstellar disks. In the earliest stages of planetary formation, microscopic dust grains stick together through electrostatic forces, building into fluffy aggregates roughly the size of snowflakes. These delicate structures continue growing through gentle collisions until they reach sizes measured in centimeters and meters. But at meter-scale sizes, the physics becomes treacherous. Objects are too large to stick together through electrostatic forces, but too small to dominate their orbital zones through gravitational attraction. Instead of continuing to grow, meter-sized objects tend to fragment when they collide, creating debris that falls back into smaller size categories. This bottleneck can persist for millions of years, preventing the formation of the kilometer-sized planetesimals that eventually grow into planets. Raymond's theoretical work identified several mechanisms that might help objects overcome the meter barrier, but most required very specific conditions or timescales that made planetary formation a rare and difficult process. Then Atlas arrived, demonstrating properties that suggested a completely different solution to the planetary formation puzzle. Interstellar objects like Atlas carry several advantages for overcoming the meter barrier. They arrive in stellar systems already assembled into kilometer-scale objects with sufficient gravitational self-attraction to avoid fragmentation during collisions. Their exotic compositions, enriched with volatile materials from different stellar environments, might provide chemical catalysts that enhance sticking efficiency when they encounter local dust and debris. Most importantly, their orbital characteristics allow them to explore regions of circumstellar disks that local materials cannot easily access. Atlas's hyperbolic trajectory carried it through our solar system at velocities and inclinations that would allow it to interact with debris across a wide range of orbital distances and angles. Raymond's model suggests that a single interstellar object like Atlas, captured into orbit around a young star, could serve as a gravitational and chemical seed that accelerates planetary formation throughout the entire circumstellar disk. The object's gravitational influence would attract surrounding dust and debris, while its volatile outgassing would provide chemical materials that enhance aggregation processes. The water vapor that Atlas produces so prodigiously might serve as a particularly effective bonding agent for cosmic dust. Water ice can act as a cement that holds silicate particles together, creating aggregates with sufficient cohesion to survive collisions that would destroy purely mechanical assemblages. The massive water vapor production that makes Atlas so mysterious in our mature solar system might represent exactly the kind of chemical seeding that young stellar disks require for efficient planetary formation. Computer simulations of circumstellar disk evolution with embedded interstellar objects reveal fascinating dynamics. The foreign objects don't simply add their own mass to the planetary formation process. They catalyze the growth of much larger masses by providing nucleation sites where local materials can aggregate more efficiently. Dr. Raymond's team modeled the capture and evolution of Atlas-like objects in young stellar systems and found that single interstellar visitors could potentially trigger the formation of planetary systems with masses dozens of times greater than the visitor itself. The interstellar object serves as a cosmic catalyst, enabling chemical and gravitational processes that would otherwise require much longer timescales or might not occur at all. This catalytic effect might explain why some stellar systems appear to have formed planets much more rapidly than conventional theories predict. Young stars surrounded by planetary systems while their circumstellar disks are still actively accreting material might have been seeded by interstellar visitors that accelerated the entire planetary formation process. The hypothesis also suggests that planetary systems might commonly contain materials and chemical signatures from multiple stellar environments. If interstellar objects regularly participate in planetary formation, then planets throughout the galaxy might harbor chemical diversity that reflects contributions from various star systems rather than purely local stellar nucleosynthesis. Atlas's unusual water vapor production, viewed through the planet seed hypothesis, becomes not an anomaly requiring explanation, but an advertisement of its potential value as a planetary formation catalyst. Young stellar systems that capture objects like Atlas might gain access to volatile inventories and chemical processing capabilities that dramatically enhance their ability to form complex planetary architectures. The implications extend to astrobiology and the search for life throughout the galaxy. If interstellar seeding accelerates planetary formation and enhances chemical diversity, then habitable worlds might be more common and more chemically complex than models based purely on local stellar processes would suggest. Life might emerge more readily on planets that inherit chemical materials from multiple stellar environments. Dr. Raymond's analysis also suggests that the galaxy might harbor vast populations of interstellar objects specifically adapted for planetary seeding roles. Atlas' extraordinary activity might represent just one example of a cosmic ecosystem where objects routinely travel between star systems, carrying materials and catalytic capabilities that enable planetary formation on scales much larger than their own masses. The water vapor streaming from Atlas into our solar system's outer regions might eventually be captured by gravitational interactions with asteroids, comets, or even outer planets. Over geological timescales, this material could be incorporated into new objects that preserve chemical signatures from Atlas's parent star system, creating a form of interstellar chemical communication that spans millions of years. Whether Atlas will be captured into a permanent orbit around our Sun, or continue its journey into interstellar space, its passage through our solar system represents a cosmic seeding event. The 40 kilograms of water vapor it releases every second might someday contribute to the formation of objects that will carry chemical messages from another star system throughout our own solar system is future evolution. In the grand process of cosmic construction, where stars birth planets and planets nurture complexity, Atlas might represent not just a visitor but a gardener, an object whose mysterious water vapor production serves purposes that operate on timescales and spatial scales far larger than human observation can directly perceive. The universe builds its largest structures from its smallest components through a process so improbable that its success borders on the miraculous. In the swirling disks of gas and dust that surround young stars, microscopic particles somehow overcome enormous odds to aggregate into planets capable of harboring oceans, atmospheres, and perhaps even life. But this cosmic construction project faces a fundamental engineering challenge that has puzzled astronomers for decades: the meter barrier. Dr. Anders Johansson, a planetary formation specialist at Lund University, has devoted much of his career to understanding why the universe's construction process nearly fails at the most crucial stage. His research revealed that objects roughly 1 meter in size occupy a deadly middle ground, where the physical forces that enable growth at smaller scales become counterproductive, while the gravitational forces that dominate at larger scales remain too weak to provide assistance. When microscopic dust grains first encounter each other in circumstellar disks, they stick together through electrostatic attraction and van der Waals forces, the same molecular scale interactions that allow gecko feet to cling to glass surfaces. These forces work efficiently for particles measured in micrometers or millimeters, enabling the formation of fluffy aggregates that gradually accumulate more material through gentle collisions. But as these aggregates grow toward meter-scale sizes, the physics becomes treacherous. Electrostatic forces weaken rapidly with increasing size, while gravitational attraction remains negligibly small for objects less massive than small mountains. Collisions between meter-sized objects tend to be destructive rather than constructive, fragmenting the carefully assembled aggregates back into smaller pieces that must begin the growth process again. Computer simulations of this process reveal a cosmic traffic jam, where countless objects reach meter-scale sizes and then remain trapped there for millions of years, unable to grow further despite constant collisions with surrounding material. The meter barrier can prevent planetary formation entirely, leaving stellar systems filled with debris that never coalesces into the kilometer-sized planetesimals needed to build planets. Johansson's theoretical work identified several mechanisms that might help objects overcome this barrier, but most required very specific conditions or extraordinarily precise timing. Gravitational instabilities in the circumstellar disk could concentrate material into dense clumps that bypass the meter barrier entirely. Electromagnetic effects might help charged particles stick together more efficiently. Specialized chemical bonding agents could provide the adhesive strength needed to survive destructive collisions. The arrival of Atlas in our solar system with its mysterious water vapor production suggested a mechanism that Johansson had never previously considered. Interstellar seeding might provide both the mass and the chemical tools needed to overcome the meter barrier in young planetary systems. Interstellar objects like Atlas arrive already assembled at kilometer scales, having successfully navigated whatever planetary formation processes characterized their birth systems. They possess sufficient gravitational self-attraction to avoid fragmentation during collisions, while their exotic chemical compositions might provide bonding agents that enhance the sticking efficiency of local materials. Most intriguingly, the massive water vapor production that makes Atlas so mysterious in our mature solar system might represent exactly the kind of chemical enhancement that young circumstellar disks require for efficient planetary formation. Water ice serves as an excellent cement for silicate particles, creating aggregates with sufficient cohesion to survive the destructive collisions that normally prevent growth beyond the meter barrier. Johansson's team developed computer models to simulate how interstellar visitors might influence planetary formation in young stellar systems. The results were striking. A single Atlas-like object, captured into orbit around a young star, could serve as both a gravitational nucleus and a chemical catalyst that accelerated planetary formation throughout the entire circumstellar disk. The process begins when the interstellar visitor's gravity starts attracting surrounding dust and debris. Unlike local meter-sized objects that fragment when they collide, the kilometer-scale visitor can capture and retain colliding material through gravitational binding. As it sweeps through the circumstellar disk, it grows rapidly by accumulating local materials while simultaneously releasing water vapor and other chemical bonding agents that enhance the sticking efficiency of nearby objects. The water vapor creates a local chemical environment where dust aggregation becomes much more efficient. Instead of fragmenting upon collision, dust-ice mixtures can stick together and continue growing even when they reach troublesome meter-scale sizes. The interstellar visitor essentially creates a bubble of enhanced chemistry within the circumstellar disk, allowing local materials to overcome the meter barrier that would otherwise trap them indefinitely. Computer simulations reveal that this process can be remarkably efficient. The interstellar visitor grows rapidly as it accumulates local material, while its chemical influence spreads throughout surrounding regions of the disk. Objects that would normally remain trapped at meter-scale sizes can grow into kilometer-scale planetesimals within thousands of years, rather than millions. The implications extend far beyond the immediate vicinity of the captured interstellar object. Planetesimals that form through interstellar-assisted chemistry carry enhanced volatile inventories that make them more effective at capturing additional material. They serve as secondary nucleation sites that accelerate planetary formation throughout the entire stellar system. Dr. Johansson's models suggest that stellar systems that receive interstellar visitors during their early formation phases might develop planetary architectures fundamentally different from systems that rely purely on local materials. The chemical diversity introduced by interstellar objects could create planets with compositions that reflect contributions from multiple stellar environments rather than purely local nucleosynthesis. This process might explain why some observed exoplanetary systems appear to have formed much more rapidly than conventional theories predict. Young stellar systems with fully formed planetary architectures might have been seeded by interstellar visitors that provided both the mass and the chemical catalysts needed to overcome the meter barrier efficiently. The hypothesis also suggests that successful planetary formation might be more common throughout the galaxy than current theories indicate. If interstellar objects routinely carry meter barrier solutions between star systems, then stellar environments that would otherwise struggle to form planets might regularly receive the chemical and gravitational assistance needed to build complex planetary architectures. Atlas's journey through our solar system, viewed through this theoretical framework, represents not just an astronomical curiosity, but a demonstration of cosmic construction processes that might operate throughout the galaxy. Its mysterious water vapor production might be advertising its potential value as a planetary formation catalyst, a capability that would be crucial in young stellar systems, but appears anomalous in our mature solar system. The 40 kilograms of water vapor that Atlas releases every second represents chemical materials that could someday contribute to overcoming the meter barrier in whatever stellar system the comet eventually approaches. Its current journey through our solar system might be just one chapter in a much longer story of interstellar chemical exchange that enables planetary formation on scales much larger than any individual object's mass. In the cosmic engineering project that builds planets from dust, interstellar visitors like Atlas might serve as the master craftsmen, objects that carry the tools and materials needed to overcome the fundamental barriers that would otherwise prevent the universe from constructing the complex worlds where chemistry can evolve into biology and perhaps even consciousness. Deep within the cosmic void, where starlight fades to whispers and temperatures hover just above absolute zero, Atlas carries its own illumination. Beyond the familiar greenish tint of excited carbon molecules that marks it as a comet, beyond the reflected sunlight that reveals its position against the star field, there lies something more mysterious, a faint internal radiance that suggests processes operating independently of external energy sources. Dr. Olivier Hainaut, observing Atlas through the European Southern Observatory's Very Large Telescope, first noticed the anomaly during long exposure imaging sessions designed to capture the comet's faint coma structure. Even when accounting for reflected sunlight, scattered light from nearby stars, and the background glow of zodiacal dust, Atlas appeared slightly brighter than theoretical models predicted. The excess brightness was subtle, perhaps 10% above expected values, but it was consistent across multiple observation periods and wavelengths. Something within Atlas was generating photons that added to the overall luminosity detected by Earth-based telescopes. The discovery of internal luminosity opened new theoretical possibilities for understanding Atlas's mysterious energy source. If the comet was literally glowing from within, then some process was converting internal energy into electromagnetic radiation that could be detected across the vast distances separating Atlas from human observation platforms. Several mechanisms could theoretically produce such internal illumination. Radioactive decay of unstable isotopes could generate energetic particles that excited surrounding materials, causing them to fluoresce at visible wavelengths. Chemical reactions between exotic materials in Atlas's interior might produce chemiluminescence similar to the cold light generated by bioluminescent organisms on Earth. More exotic possibilities included cosmic ray interactions with unusual materials within Atlas's structure, creating particle cascades that terminated in photon emission. If the comet harbored any ferromagnetic materials, interactions with the interplanetary magnetic field might generate electrical currents that produced thermal emission detectable as faint infrared radiation. Dr. Haynott's team conducted detailed spectroscopic analysis of the excess emission, searching for spectral lines that might identify the specific physical processes responsible for Atlas's internal glow. The spectrum proved frustratingly featureless, a smooth continuum that provided few clues about its origin. The lack of distinct spectral features suggested that the internal luminosity arose from thermal processes rather than specific atomic or molecular transitions. Something within Atlas was being heated to temperatures sufficient to produce black body radiation detectable by sensitive instruments, but the heating mechanism remained completely mysterious. Thermal modeling of Atlas' interior revealed the challenge of maintaining elevated temperatures in the cold depths of interplanetary space. At the comet's distance from the Sun, any internal heat source would need to overcome rapid radiative cooling through the object's surface. The mathematics of heat transfer suggested that significant internal energy production would be required to maintain temperatures even a few degrees above the background equilibrium. Yet the observed internal luminosity implied the presence of exactly such an energy source. Something within Atlas was generating heat at rates sufficient to warm internal materials and drive thermal emission that contributed measurably to the comet's overall brightness. The connection between internal heating and massive water vapor production became increasingly apparent as researchers analyzed the observational data. If internal processes were generating enough energy to produce detectable thermal emission, they might also be providing the energy needed to drive sublimation of water ice at rates far exceeding what solar heating alone could account for. Dr. Dennis Bodowitz, analyzing the correlation between Atlas's brightness variations and water vapor production rates, found intriguing patterns that suggested common underlying processes. Periods of enhanced internal luminosity coincided with increased water vapor release, while dimmer phases corresponded to reduced outgassing activity. This correlation implied that whatever mechanism was responsible for Atlas's internal glow was also driving its extraordinary water vapor production. The energy budget that had seemed impossible when considering only solar heating became more plausible when internal energy sources were included in the calculations. But identifying the nature of these internal processes remained elusive. Conventional radioactive decay would provide steady energy output that shouldn't vary significantly over the timescales of astronomical observation. Yet Atlas's internal luminosity showed periodic variations that suggested more dynamic processes. Some theoretical models proposed that Atlas might harbor cristobalite or other crystalline phases that underwent exothermic phase transitions when subjected to thermal cycling or mechanical stress. As the comet rotated and different regions experienced varying solar heating, internal stresses might trigger crystalline phase changes that released stored energy in organized pulses. Other models suggested that Atlas might contain metastable chemical compounds that had been preserved during millions of years of interstellar wandering, but became reactive when exposed to the chemical environment of our solar system. Interactions with the solar wind or interplanetary dust might trigger cascading chemical reactions that generated both thermal energy and the exotic chemistry needed to drive massive water vapor production. The most speculative theories proposed that Atlas's internal glow might indicate the presence of materials or processes that operated according to physical principles not yet fully understood by human science. If the comet had formed in an environment with access to unusual chemical species or physical conditions, it might harbor energy sources that had no direct analogs in terrestrial or solar system chemistry. High-resolution imaging revealed that Atlas's internal luminosity wasn't uniformly distributed throughout its structure. Certain regions appeared to glow more brightly than others, creating brightness asymmetries that rotated with the comet's spin period. These variations suggested that the internal energy sources were localized rather than globally distributed. The localized nature of the internal luminosity provided additional clues about possible heating mechanisms. If radioactive materials were responsible, they would likely be concentrated in specific mineralogical phases or structural domains within the comet's interior. If chemical reactions were involved, they might be occurring preferentially in regions where different materials came into contact, or where thermal gradients created optimal reaction conditions. As Atlas continued its journey through the solar system, its internal glow persisted with remarkable consistency. Unlike the brightness variations that might be expected from external heating sources, the internal luminosity maintained steady baseline levels punctuated by organized variations that suggested internal processes operating according to their own temporal rhythms. The persistence of internal illumination far from the Sun supported theories that Atlas possessed genuinely independent energy sources, rather than simply exhibiting enhanced efficiency in converting solar energy to thermal radiation. Whatever was causing the comet to glow from within appeared to be self-sustaining and potentially capable of operating indefinitely during its journey through interstellar space. In the vast darkness between stars where external energy sources dwindled to negligible levels, Atlas would carry its internal flame like a cosmic lighthouse, a beacon powered by processes that remained mysteriously beyond human understanding, but tantalizingly within the realm of future discovery. In the precise language of thermodynamics, energy cannot be created or destroyed, only transformed from one form to another according to laws that govern every process from stellar fusion to the beating of a human heart. These conservation principles have never been violated in centuries of careful scientific observation, making them among the most trusted foundations of physical science. Yet Atlas appeared to be operating an internal engine that challenged these fundamental assumptions about how energy behaves in the cold depths of space. Dr. Cyrielle Opetom, leading the theoretical analysis of Atlas's energy budget, found herself confronting calculations that simply refused to balance according to conventional physics. No matter how she adjusted the parameters or considered alternative energy sources, the mathematics consistently indicated that Atlas was converting more energy into water vapor production than any known mechanism could provide. The problem began with basic thermodynamics. Converting 40 kilograms of water ice to vapor every second requires approximately 120 megajoules of energy, equivalent to the power output of a small electrical generating station. This energy must overcome the latent heat of sublimation, while also providing the kinetic energy needed to accelerate water molecules to escape velocity from Atlas's weak gravitational field. Solar heating at Atlas's distance from the Sun could provide at most 10 megajoules per second, assuming perfect absorption efficiency and optimal surface orientation. Even this theoretical maximum fell short of observed requirements by more than an order of magnitude, leaving 110 megajoules per second that had to originate from internal sources. Conventional internal energy sources proved equally inadequate. Radioactive decay of uranium-238 and thorium-232, the most abundant long-lived radioactive isotopes, would need to be present in concentrations of roughly 10% by mass to provide sufficient energy output. Such concentrations would make Atlas essentially a dirty bomb, which seemed inconsistent with its apparent structural stability and organized outgassing patterns. Crystalline phase transitions could theoretically release stored energy as amorphous water ice converted to crystalline forms, but the total energy available through such processes was limited by the amount of amorphous ice present in Atlas's structure. Even if the entire comet consisted of metastable ice, the available energy would be exhausted within days or weeks of sustained outgassing. Chemical energy from exotic reactions faced similar limitations. The most energetic chemical processes release at most a few electron volts per molecule, sufficient for modest heating but inadequate for the industrial-scale energy production that Atlas's water vapor release required. Dr. Opetom began exploring increasingly exotic theoretical possibilities. Could Atlas harbor materials that underwent nuclear reactions under conditions present in its interior? Fusion reactions required temperatures of millions of degrees, while fission needed critical masses of specific isotopes. Neither seemed plausible for a comet-sized object operating at temperatures barely above absolute zero. Perhaps cosmic ray interactions could create cascade processes that amplified energy deposition within Atlas's structure. High-energy particles from interstellar space constantly bombarded the comet's surface, potentially triggering nuclear reactions in trace elements or creating exotic particles that decayed with energy release. But detailed calculations showed that cosmic ray energy deposition rates were orders of magnitude too small to account for observed phenomena. The energy crisis deepened when researchers realized that Atlas's extraordinary performance was sustained rather than transient. A single burst of exotic energy might be explained by unusual circumstances or measurement errors, but Atlas maintained its impossible energy output across observation periods spanning multiple months. This consistency ruled out most exotic explanations that depended on rare events or unstable processes. Whatever was powering Atlas's internal engine appeared to be drawing from energy reserves that were both massive and reliably accessible. Dr. Alan Fitzsimmons, contributing independent analysis from Queen's University Belfast, proposed that Atlas might represent a new class of object that operated according to physical principles, not yet incorporated into standard thermodynamic frameworks. If the comet had formed in an environment with access to energy sources or storage mechanisms unknown to terrestrial science, its behavior might appear impossible only because human understanding remained incomplete. This perspective shifted the theoretical focus from explaining how Atlas violated known physics to discovering what unknown physics might account for its observed behavior. Rather than an impossibility requiring exotic explanations, Atlas might be demonstrating natural processes that operated according to consistent principles awaiting human discovery. Some theoretical models explored whether Atlas might be accessing energy from quantum vacuum fluctuations, the constant creation and annihilation of virtual particles that fill apparently empty space. If the comet's internal structure created conditions that allowed extraction of zero-point energy, it might theoretically tap into energy sources that appeared unlimited from human perspective. Other models investigated whether Atlas might be converting matter directly to energy through processes more efficient than conventional chemical or nuclear reactions. If the comet harbored exotic matter states or participated in reactions that violated apparent conservation principles, it might access energy sources that conventional physics considered impossible. The most radical theoretical framework suggested that Atlas might be demonstrating technologies rather than natural processes, that its internal engine represented artificial energy sources deployed by intelligence operating on scales beyond current human capability. This interpretation reframed the energy crisis as evidence of engineering, rather than violation of physical law. Regardless of the specific mechanism, Atlas's sustained energy output suggested that the universe might harbor energy sources or storage systems that human science had never encountered. The comet's internal engine might be advertising the existence of physical processes that operate according to principles awaiting discovery by future generations of researchers. As Atlas continued its journey through the solar system, its impossible engine maintained steady operation with the reliability of a fundamental force. Whether natural or artificial, its energy source appeared to be self-sustaining and potentially inexhaustible. A cosmic power plant that challenged humanity's understanding of what was possible in a universe governed by conservation laws. The engine that shouldn't be possible continued operating with serene indifference to human theoretical limitations, converting unknown energy sources into massive water vapor production that painted Atlas as signature across the cosmos, with the bold strokes of processes that transcended current scientific understanding. In the careful ecology of scientific discourse, certain ideas occupy precarious niches where they survive, not because they are widely accepted, but because they serve essential functions in maintaining intellectual diversity. Dr. Avi Loeb's suggestion that interstellar objects might sometimes be artificial rather than natural has established such a niche, controversial enough to attract criticism, but valuable enough to persist as a check against premature theoretical closure. When Atlas arrived with its impossible energy budget and mysterious water vapor production, Loeb's alien craft hypothesis gained new relevance. Here was an object that appeared to violate fundamental principles of thermodynamics, while exhibiting behaviors that seemed more technological than geological. If ever there was a candidate for artificial origin, Atlas presented compelling arguments. The case for artificial intelligence began with energy considerations. Atlas's sustained production of 40 kilograms of water vapor per second required energy sources that exceeded any known natural mechanism by orders of magnitude. While this energy crisis posed problems for natural explanations, it would be easily resolved if Atlas possessed artificial power sources operating according to principles beyond current human understanding. Advanced technological civilizations might have access to energy sources that appear impossible from humanity's current perspective. Zero-point energy extraction, matter-antimatter annihilation, or controlled fusion reactions could theoretically provide the massive energy output that Atlas demonstrated without requiring exotic natural processes or violation of physical conservation laws. The organized nature of Atlas's water vapor jets provided additional evidence for artificial origins. Rather than the chaotic outgassing typical of natural sublimation processes, Atlas exhibited structured jets that pulsed with organized rhythms, suggesting internal control mechanisms. Such precision might indicate engineered systems designed to produce specific effects rather than random natural processes. Dr. Loeb's analysis focused particularly on the strategic timing and targeting of Atlas's appearance in the solar system. The comet arrived at optimal distances for detailed observation, maintained high activity levels throughout its passage, and displayed spectroscopic signatures that advertised its exotic nature to any technological civilization capable of detecting them. This combination of factors seemed too convenient to be entirely coincidental. If Atlas were a natural object, its behavior during passage through our solar system would likely be determined by physical processes that paid no attention to human observational capabilities. But if it were artificial, its activities might be specifically designed to attract attention and communicate information about its creator's technological capabilities. The communication hypothesis suggested that Atlas's water vapor production might serve as a form of cosmic semaphore, a signaling system designed to convey information through organized patterns of material release. Each burst of water vapor might encode data about the object's origin, purpose, or technological specifications, using protocols that humanity was only beginning to recognize. Loeb proposed that advanced civilizations might routinely dispatch probe objects throughout the galaxy, using interstellar trajectories to survey star systems and search for emerging technological civilizations. Such probes would need to operate autonomously for millions of years while traversing the vast distances between stars, requiring self-sustaining power sources and robust communication systems. Atlas's extraordinary performance might indicate exactly such technological sophistication. Its internal energy source provided sufficient power for sustained operations across interstellar distances, while its water vapor production created observable signatures that would attract attention from any civilization capable of spectroscopic analysis. The probe hypothesis also addressed puzzling aspects of Atlas's chemical composition. Rather than exhibiting the uniform material distribution typical of natural objects, Atlas appeared to harbor distinct chemical domains that produced different types of outgassing. Such heterogeneity might reflect engineered systems designed to serve specific technological functions rather than natural accretion processes. Advanced materials science might enable the construction of objects that appeared comet-like while harboring sophisticated internal systems. Artificial comets could serve as ideal camouflage for technological devices, providing naturally explainable cover for activities that might otherwise attract unwanted attention or interference. Critics of the alien craft hypothesis pointed out that extraordinary claims required extraordinary evidence, and Atlas's behavior, while unusual, didn't definitively rule out natural explanations. Unknown natural processes might account for the comet's energy budget without requiring artificial intelligence or advanced technology. Dr. Dennis Bodowitz, while acknowledging the energy budget problems that made artificial hypotheses attractive, maintained that scientific methodology required exhausting natural possibilities before considering technological alternatives. We should be very careful about invoking alien technology to explain phenomena that might simply reflect gaps in our understanding of natural processes, he cautioned. The debate highlighted fundamental questions about how science should respond to observations that challenged established theoretical frameworks. Conservative approaches emphasized the importance of maintaining consistency with known physical principles, while more speculative perspectives argued that unprecedented observations might require unprecedented explanations. Loeb's contribution to this debate wasn't primarily about convincing the scientific community that Atlas was artificial, but rather about ensuring that artificial possibilities receive systematic consideration rather than reflexive dismissal. His analysis forced researchers to articulate precisely what evidence would be required to distinguish artificial from natural interstellar objects. The alien craft hypothesis also raised profound questions about the prevalence and detectability of technological civilizations throughout the galaxy. If objects like Atlas represented routine survey missions by advanced civilizations, then the galaxy might be far more populated with intelligence than traditional estimates suggested. Such scenarios would have enormous implications for humanity's understanding of its place in the cosmic community. Contact with alien intelligence might not require dramatic encounters with obviously technological objects, but could instead emerge gradually through careful analysis of subtly artificial phenomena that initially appeared natural. Whether Atlas was artificial or natural, its extraordinary behavior demonstrated that the universe harbored processes operating according to principles that human science was only beginning to understand. The alien craft debate served to ensure that this investigation would be comprehensive, considering possibilities that might otherwise be overlooked due to theoretical conservatism or anthropocentric assumptions. In the cosmic conversation between intelligence and natural phenomena, Atlas had arrived as either a natural process that challenged human understanding of physics, or an artificial process that challenged human understanding of intelligence itself. The debate would continue until evidence emerged that definitively resolved the question, or until humanity developed the theoretical sophistication needed to understand how nature might accomplish what currently appeared impossible. Across the spiral arms of the Milky Way, in the vast spaces between stars where darkness reigns and temperatures hover just above absolute zero, a patient diaspora unfolds. Millions of objects like Atlas drift through the interstellar medium on journeys that span geological epochs, carrying with them the chemical signatures of distant worlds and the potential to influence planetary formation in star systems they will never see. This is the universe's cosmic gardener, a cosmos that plants the seeds of worlds with the same systematic persistence that terrestrial gardeners scatter flower seeds across prepared soil. Each interstellar wanderer represents a potential catalyst for planetary formation, a cosmic seed that carries both the materials and the chemical processes needed to accelerate the construction of new worlds around distant suns. Dr. Amaya Moro-Martin, whose research focuses on the population dynamics of interstellar objects, has developed statistical models that suggest the galaxy might harbor trillions of objects similar to Atlas. These wanderers represent the natural outcome of planetary formation processes that routinely eject material from young star systems, creating a vast population of interstellar nomads that traverse the galaxy over cosmic timescales. The numbers are staggering in their implications. If each star system ejects roughly 1% of its initial solid material during planetary formation, a conservative estimate based on computer simulations, then the galaxy should contain more interstellar objects than stars. Most would be small, dark, and undetectable from human observation platforms, but they would collectively represent a vast reservoir of processed materials flowing between stellar systems. Atlas belongs to a subset of this population that remains active during interstellar travel. Its extraordinary water vapor production and exotic energy sources mark it as potentially more valuable for planetary seeding than passive debris that would simply add mass to circumstellar disks without providing chemical catalysts or energy sources. The cosmic seeding hypothesis suggests that objects like Atlas serve essential functions in galactic ecology. They transport chemical diversity between star systems, while providing the tools needed to overcome barriers that might otherwise prevent efficient planetary formation. Their water vapor production, rather than being mysterious or anomalous, represents exactly what young circumstellar disks require for rapid assembly of complex planetary architectures. Computer simulations of galactic chemical evolution reveal how this seeding process might operate on cosmic scales. Star systems that capture interstellar visitors during their early formation phases develop planetary architectures enriched with materials from multiple stellar environments. The resulting planets harbor chemical signatures that reflect contributions from various nucleosynthetic processes, rather than purely local stellar chemistry. This chemical mixing might be essential for the development of habitable worlds. Planets that form from purely local materials are limited to the chemical inventory available from their host star's nucleosynthetic history. But planets that incorporate materials from interstellar visitors gain access to chemical diversity that reflects the entire galaxy's stellar evolution processes. The biological implications are profound. Life as we understand it requires access to specific combinations of chemical elements and compounds that might not be available in all stellar environments. Systems that receive interstellar seeding might be more likely to develop the chemical foundations needed for biological evolution, while isolated systems might lack essential materials despite otherwise favorable conditions. Dr. Mauro Martins' population model suggests that star systems receive interstellar visitors with remarkable frequency on astronomical timescales. Young stellar systems might capture several Atlas-like objects during their first few million years, when circumstellar disks are still actively forming planets. Each visitor would contribute its own chemical inventory, while catalyzing more efficient utilization of local materials. The seeding process might also explain observed patterns in exoplanetary system architectures. Some stellar systems appear to have formed planets much more rapidly than conventional theories predict, while others show unusual chemical abundances that don't match their host stars' compositions. Both phenomena could result from interstellar seeding events that provided both materials and catalytic processes. Atlas's journey through our solar system represents one chapter in this vast galactic narrative. Its current passage near Earth allows humanity to observe cosmic seeding processes that operate throughout the galaxy, but are normally invisible due to the vast distances involved in interstellar travel. The 40 kilograms of water vapor that Atlas releases every second might eventually be incorporated into objects throughout our solar system's outer regions. Kuiper belt objects, Oort cloud comets, or even moons of the outer planets could capture and preserve materials that originated in Atlas's parent star system. Future human exploration of these objects might discover chemical signatures that serve as direct samples of interstellar chemistry. The cosmic seeding hypothesis also suggests that Earth itself might harbor materials contributed by ancient interstellar visitors. During the first billion years of solar system history, when planetary formation was still active and the impact rate was much higher than today, captured interstellar objects might have delivered chemical materials that became incorporated into Earth's geology or even its early biosphere. Some researchers have proposed that life's origin on Earth might have been facilitated by chemical diversity contributed through interstellar seeding. Organic compounds preserved in interstellar objects could have provided the chemical starting materials needed for biological evolution, while exotic chemical processes might have catalyzed reactions that would otherwise require extraordinary coincidences. The search for life throughout the galaxy might need to consider cosmic seeding as a fundamental process that influences the chemical environment available for biological evolution. Rather than assuming that life must emerge from purely local chemistry, astrobiology might need to account for the chemical mixing that results from billions of years of interstellar material exchange. Atlas's mysterious energy sources and organized water vapor production, viewed through the cosmic seeding framework, become advertisements of its potential value for planetary formation processes. Its current journey through our mature solar system provides human science with an opportunity to study seeding mechanisms that might be operating throughout the galaxy. As Atlas continues toward the outer solar system and eventually returns to interstellar space, it carries with it samples of our solar system's chemical environment that will be transported to whatever stellar system it eventually encounters. In cosmic terms, it serves as both a seed arriving from distant origins and a gardener collecting materials for future planting in stellar systems yet to be born. The universe that plants worlds operates according to timescales that dwarf human experience and spatial scales that challenge human imagination. But in the patient drift of objects like Atlas between the stars, we glimpse the cosmic processes that have been shaping galactic chemistry and planetary formation for billions of years. processes that may have contributed to the very conditions that enabled life to emerge on Earth, and might be enabling similar emergence throughout the galaxy. In the careful architecture of scientific progress, skepticism serves as both foundation and guardian. Not an obstacle to discovery, but its most essential protector. While theoretical speculation explores the boundaries of possibility, skeptical analysis ensures that extraordinary claims face extraordinary scrutiny before they reshape our understanding of the cosmos. For Atlas, with its impossible energy budget and mysterious water vapor production, skeptical voices provide crucial balance against the intoxication of unprecedented observations. Dr. Nalin Samarasina, a comet dynamics specialist at the Planetary Science Institute, has spent decades studying the subtle mechanisms that drive outgassing in conventional solar system comets. His expertise in comet behavior makes him uniquely qualified to evaluate whether Atlas's extraordinary performance might result from natural processes operating under extreme conditions, rather than exotic energy sources or artificial intelligence. Samarasina's analysis begins with a fundamental principle. Extraordinary phenomena often result from ordinary processes operating under extraordinary circumstances. Rather than invoking unknown physics or alien technology, careful investigation might reveal that Atlas's behavior reflects familiar comet mechanisms pushed to extreme efficiency by unusual but natural conditions. The water vapor production that seems to violate thermodynamic constraints might result from exceptional solar energy absorption and retention rather than independent energy sources. If Atlas possessed unusually dark surface materials with absorption coefficients approaching theoretical limits, it might capture and convert solar radiation with efficiency, far exceeding typical comet performance. Surface roughness could enhance energy absorption through multiple scattering that trapped photons within surface structures, rather than reflecting them back to space. Microscopic surface features might create cavity resonators that concentrated electromagnetic energy, achieving local heating effects far beyond what smooth surface models would predict. Internal structure might also contribute to exceptional performance. If Atlas harbored extensive networks of subsurface cavities or channels, solar heating might penetrate much deeper into its interior than conventional models assumed. Enhanced heat conduction through unusual mineral compositions could distribute energy throughout larger volumes, driving water vapor production from internal ice reservoirs rather than purely surface sublimation. Dr. Samarasina points out that Atlas's interstellar origin might have exposed it to chemical and physical processing that created surface properties unknown in solar system objects. Millions of years of cosmic ray bombardment exposure to varying stellar radiation fields and thermal cycling during passage through different stellar environments might have produced surface compositions or structures that operated according to different physical principles than locally formed comets. Chemical weathering during interstellar travel could have created surface materials with catalytic properties that enhanced sublimation efficiency. Exotic chemical species produced by cosmic ray interactions might lower the activation energy needed for phase transitions, allowing water ice to sublimate at temperatures where it would normally remain solid. The organized nature of Atlas's outgassing, rather than indicating artificial control systems, might reflect natural structural features created during its formation or subsequent evolution. Subsurface pressure buildup from thermal processing could create jets and geysers that operated according to fluid dynamics principles, rather than technological design. Many solar system comets exhibit highly organized outgassing patterns that result from internal structural controls, rather than external heating uniformity. Atlas's jets might simply represent extreme examples of such natural organization, appearing artificial only because their scale and persistence exceeded previous observations. Skeptical analysis also addresses the temporal aspects of Atlas's performance. Rather than sustained energy output that violated conservation principles, careful accounting might reveal that the comet was simply releasing energy stored during its formation or accumulated during millions of years of interstellar wandering. Crystalline phase transitions could theoretically store vast amounts of energy in metastable configurations that remained stable during interstellar travel, but became accessible when triggered by solar system environmental conditions. Atlas might be powered by its own geological history rather than ongoing energy production. Dr. Samarasina emphasizes that skeptical analysis does not seek to diminish Atlas's significance, but rather to ensure that its interpretation rests on solid theoretical foundations. If natural processes could account for the comet's behavior, then scientific understanding would be advanced through better comprehension of extreme comet physics, rather than revolution of fundamental principles. The skeptical perspective also highlights the importance of observational precision in distinguishing between genuinely impossible phenomena and merely improbable ones. Measurement uncertainties, instrumental limitations, and systematic errors could potentially account for some of the discrepancies between Atlas's observed behavior and theoretical predictions. Improved observations with next-generation instruments might reveal that Atlas's energy budget, while remarkable, operated within the boundaries of known physics, when all energy sources and loss mechanisms were properly accounted for. Precision spectroscopy might identify chemical processes that explained both the water vapor production and the apparent energy surplus. The role of skepticism in evaluating Atlas extends beyond specific technical questions to encompass broader issues about how science responds to anomalous observations. History provides numerous examples of phenomena that appeared to violate fundamental principles, but were eventually explained through more sophisticated application of known physics rather than discovery of new physical laws. Skeptical analysis serves essential quality control functions that protect scientific understanding from premature revision based on incomplete data or theoretical speculation. While maintaining openness to genuinely revolutionary discoveries, skepticism ensures that extraordinary claims face the rigorous testing they deserve. For Atlas, skeptical scrutiny has already identified several natural mechanisms that might contribute to its extraordinary performance. Whether these mechanisms prove sufficient to explain all observed phenomena remains an open question, but their systematic evaluation ensures that any remaining mysteries rest on solid observational foundations rather than theoretical speculation. The skeptic's reminder that natural explanations deserve exhaustive exploration before exotic alternatives are considered does not diminish the wonder and excitement generated by Atlas's remarkable behavior. Instead, it ensures that this wonder is channeled into productive scientific investigation that advances human understanding through careful observation and rigorous analysis rather than speculative leaps. In the cosmic conversation between observation and theory, skepticism serves as translator, ensuring that the messages encoded in Atlas's water vapor are read with sufficient care and precision to distinguish genuine cosmic secrets from the artifacts of human theoretical limitations or observational uncertainties. At the very limits of human technological capability, where individual photons arrive like cosmic whispers after traveling millions of kilometers through space, the most sensitive instruments ever constructed continue their patient dialogue with Atlas. Each particle of light carries encoded information about processes occurring in the cold depths of the outer solar system, data that requires extraordinary precision to detect and interpret. The Swift Observatory, humanity's most capable ultraviolet telescope, maintains its vigil even as Atlas fades toward the detection threshold. Dr. Dennis Bodowitz and his international team push their instruments to operational limits, extracting meaningful signals from observations where noise begins to dominate over actual astronomical data. At these extreme distances, conventional astronomical observation becomes an exercise in statistical archaeology. Individual measurements might be ambiguous or corrupted by instrumental effects, but careful accumulation of data across multiple observation periods can reveal patterns that emerge from the noise like ancient inscriptions, gradually becoming legible under patient scholarly attention. The ultraviolet signatures of hydroxyl radicals that first revealed Atlas's extraordinary water vapor production continue to flicker at the edge of detectability. Each photon of OH emission that reaches Swift's detectors represents thousands of water molecules that underwent photodissociation in the vicinity of Atlas, creating a statistical sampling of the comet's ongoing activity. But the interpretation of these fading signals requires increasingly sophisticated analysis techniques. As Atlas recedes from the Sun, its water vapor production should decline according to well-established relationships between heliocentric distance and comet activity. The fact that detectable signals persist at distances where conventional comets would fall silent provides continuing evidence of the object's anomalous behavior. Ground-based telescopes contribute complementary observations that fill gaps in space-based coverage. The Very Large Telescope, the Keck Observatory, and other premier facilities allocate precious observing time to tracking Atlas, even when the scientific return diminishes due to the comet's fading brightness. Dr. Cyrielle Opitom coordinates these ground-based campaigns with the dedication of an astronomer who recognizes that Atlas represents a once-in-a-lifetime opportunity to study an active interstellar object. Each observation period might be the last chance to detect specific spectral signatures or measure critical physical parameters before the comet fades beyond the reach of human instrumentation. The data streams flowing from these diverse observation platforms create a complex portrait of Atlas's evolution as it moves away from the Sun. Rather than the simple decline in activity that would characterize a conventional comet, Atlas exhibits temporal variations that suggest internal processes continuing to operate independently of solar heating. Brightness fluctuations persist with periodicities that match Atlas's rotation period, indicating that localized active regions continue producing detectable outgassing even at vast distances from the Sun. These variations provide crucial information about the spatial distribution of whatever energy sources power the comet's ongoing activity. Spectroscopic analysis reveals that Atlas's chemical signature evolves as it recedes from the solar system. While water vapor remains the dominant outgassing product, trace amounts of other chemical species appear and disappear in patterns that suggest complex internal chemistry operating according to its own kinetic laws. Some researchers interpret these chemical variations as evidence of staged shutdown processes, different internal energy sources exhausting their reserves or becoming inactive as thermal conditions change during Atlas's journey into the outer solar system. Others propose that the chemical evolution reflects ongoing reactions that continue processing materials within the comet's interior. The radio telescopes that can detect water vapor directly through microwave emission lines provide the most reliable measurements of Atlas's total outgassing rate. These observations are less subject to atmospheric interference and instrumental systematic errors than optical or ultraviolet measurements, creating a robust foundation for understanding the comet's energy budget even as it approaches detection limits. Dr. Martin Cordner, coordinating radio observations from multiple facilities, describes the challenge of detecting Atlas's water vapor signature as listening for whispers in a cosmic hurricane. The sensitivity required to measure water emission from such distances pushes radio astronomy to its operational limits, requiring integration times measured in hours to accumulate sufficient signal for meaningful analysis. Yet these painstaking radio observations continue to detect water vapor production at levels that exceed theoretical predictions based on solar heating alone. The persistence of water emission at large heliocentric distances provides some of the strongest evidence that Atlas possesses internal energy sources that operate independently of external heating. The combined data from all observation platforms create a comprehensive database that will serve as a reference for interpreting future interstellar visitors. Atlas's behavior across the full range of solar system distances provides calibration data for understanding how interstellar objects might typically behave when they encounter stellar heating. But the data also preserve evidence of Atlas's unique characteristics. The specific energy sources, chemical compositions, and physical processes that distinguish it from both conventional solar system comets and other interstellar visitors like Oumuamua and Borisov. Statistical analysis of the accumulated observations reveals correlations and patterns that weren't apparent in individual data sets. The relationship between water vapor production, internal luminosity, and surface activity variations creates a multidimensional portrait of Atlas's behavior that suggests underlying physical processes more complex than simple thermal response to solar heating. As Atlas continues to recede and signals fade toward undetectability, the data streams become increasingly precious. Each successful observation might represent the final measurement of specific physical parameters before they fall below the sensitivity thresholds of human instrumentation. The transition from active observation to data analysis marks a crucial phase in the scientific investigation of Atlas. The observational campaigns have accumulated unprecedented data about an active interstellar object, but the interpretation of this data will require years of theoretical development and computational modeling. The whispers from the edge that these final observations capture carry information about cosmic processes that operate on scales and according to principles that humanity is only beginning to understand. Each photon represents a data point in humanity's growing database of interstellar object properties, a database that will guide the search for and interpretation of future visitors from other star systems. In the dialogue between human technology and cosmic phenomena, Atlas's fading signals mark not an ending but a transformation. From active observation to theoretical synthesis, from data collection to understanding from mystery, to the gradual emergence of new knowledge about how the universe creates and sustains complex objects that traverse the vast spaces between stars. In the patient rhythm of cosmic time, where stellar lifetimes are measured in billions of years, and galactic rotations span hundreds of millions, the universe practices a form of recycling so thorough and elegant that it transforms death into the foundation for new life. Stars are born, live, and die in cycles that scatter their nuclear-forged elements across interstellar space, where gravity and chemistry begin the patient process of assembling new worlds from the debris of ancient suns. Atlas represents one chapter in this vast recycling narrative, a wandering fragment that carries within its frozen structure the chemical heritage of stellar processes that operated before our own sun began shining. Its water, its organic compounds, its silicate dust, all were forged in the nuclear furnaces of stars that died long ago, their material heritage preserved in the cold storage of interstellar objects that drift between star systems like cosmic seed banks. The hydrogen atoms locked within Atlas's water molecules were created in the first moments after the Big Bang, when the universe was young and simple. But the oxygen atoms that complete those H2O molecules were manufactured much later, in the core of a massive star that fused helium nuclei into carbon, carbon into oxygen, and oxygen into heavier elements through the patient alchemy of nuclear fusion. When that ancient star exhausted its nuclear fuel, it died in a supernova explosion that scattered these oxygen atoms across light years of space, mixing them with hydrogen gas and cosmic dust to create the raw materials from which new star systems could form. Some of this material eventually condensed into the circumstellar disk where Atlas originated, carrying the chemical signature of stellar death and transformation into the construction materials for new worlds. Dr. Alan Boss, whose computer simulations model the formation and evolution of planetary systems, describes interstellar objects like Atlas as cosmic recycling bins, repositories that preserve and transport materials between star systems, enabling chemical mixing on galactic scales that would otherwise be impossible. The process operates with the patient efficiency of a fundamental force. Stellar winds from dying stars push processed materials into interstellar space, where they mix with gas and dust from other sources. Gravitational interactions and galactic rotations stir this interstellar medium, creating chemical gradients and density variations that influence where and how new stars form. When gravitational collapse eventually creates new stars from this enriched material, the resulting circumstellar disks inherit chemical diversity that reflects contributions from many previous stellar generations. Planets that form from such material harbor elements and compounds that originated in dozens or hundreds of different stars, creating worlds with access to chemical complexity that far exceeds what any single star could produce. Atlas's journey through our solar system represents one link in this vast chain of cosmic recycling. The materials it carries originated in another star system, were preserved during millions of years of interstellar wandering, and now contribute their chemical inventory to our own solar system's environment through the 40 kilograms of water vapor released every second. This material doesn't simply vanish into space. Some fraction will be captured by gravitational interactions with asteroids, comets, or outer planets, becoming incorporated into objects that will preserve Atlas's chemical signature for billions of years. Future human exploration of the outer solar system might discover ice deposits or organic compounds that originated in Atlas's parent star system. The recycling process also operates in reverse. As Atlas passes through our solar system, it captures trace amounts of material from the solar wind, interplanetary dust, and possibly even atmospheric escape products from planets. When it eventually arrives at another star system millions of years from now, it will carry samples of our solar system's chemical environment as part of its growing inventory of interstellar materials. This two-way exchange creates a galactic-scale mixing process that has been operating for billions of years. Every star system both contributes to and receives materials from this cosmic recycling network, creating chemical connections between worlds separated by vast distances and time intervals. The biological implications are profound. Earth's oceans, atmosphere, and living organisms are constructed from materials that originated in hundreds of different stars across billions of years of cosmic history. The calcium in human bones was forged in supernova explosions. The iron in hemoglobin was created in stellar cores. The carbon that forms the backbone of DNA was manufactured through nuclear fusion processes in ancient stars. Atlas carries similar materials, the chemical heritage of stellar evolution from another part of the galaxy. Its water molecules, organic compounds, and trace elements represent samples of cosmic chemistry that developed under different conditions, around different stars, during different epochs of galactic evolution. The cosmic recycling process ensures that no stellar death is truly final. The elements created through stellar nucleosynthesis survive their parent stars, traveling through interstellar space to participate in new cycles of planetary formation and possibly biological evolution. Each generation of stars builds upon the chemical legacy of previous generations, creating increasingly complex chemistry as the universe ages. Dr. Boss's simulations reveal how this recycling process accelerates over cosmic time. Early stellar generations had access only to hydrogen and helium, limiting the complexity of worlds they could create. But as successive generations of stars lived and died, the interstellar medium became enriched with heavier elements that enabled more complex planetary architectures and chemical environments. Objects like Atlas serve as the vehicles for this enrichment process, carrying processed materials between star systems and enabling chemical mixing that would otherwise require direct physical contact between stellar environments. The galaxy's chemical evolution depends on these wandering messengers that preserve and transport stellar heritage across the vast scales of interstellar space. The water vapor streaming from Atlas into our solar system's outer regions represents one moment in this eternal process of cosmic renewal. The molecules being released will eventually participate in new cycles of accretion and chemistry, possibly contributing to the formation of objects that will carry their chemical signature to other star systems in the distant future. As Atlas continues its journey toward interstellar space, it exemplifies the universe's commitment to renewal and recycling. Nothing is truly lost in cosmic evolution, only transformed, transported, and incorporated into new cycles of creation that connect the past, present, and future of galactic chemical evolution. In the patient rotation of cosmic recycling, death becomes life, endings become beginnings, and the debris of ancient stars becomes the foundation for new worlds where chemistry might someday evolve into biology, and biology into consciousness, capable of contemplating the cosmic processes that created the conditions for its own existence. At the boundary where scientific observation meets philosophical contemplation, Atlas presents humanity with questions that transcend the technical details of water vapor production and energy budgets. If this wandering object represents a cosmic gardener distributing the seeds of worlds, what does that tell us about the nature of existence in a universe where matter and information flow freely between star systems? The philosophical implications ripple outward from Atlas's mysterious behavior, like waves in a cosmic pond. If interstellar objects routinely carry chemical materials between star systems, then the traditional boundaries that separate one world from another become permeable membranes rather than absolute barriers. Earth's biosphere might harbor materials that originated around distant stars, while our solar system's chemical signature spreads throughout the galaxy through wanderers like Atlas. This perspective dissolves the isolation that has characterized human thinking about our place in the cosmos. We are not inhabitants of a closed system orbiting an isolated star, but participants in a galactic ecosystem where materials, energy, and information circulate through networks that connect every star system to every other across the vast scales of space and time. Dr. Sarah Seeger, whose work on exoplanet atmospheres has revealed the extraordinary diversity of worlds throughout the galaxy, reflects on how objects like Atlas challenge anthropocentric assumptions about planetary uniqueness. If the same materials that built Earth are being distributed throughout the galaxy by interstellar visitors, she observes, then the chemical foundations for life might be far more widespread than we ever imagined. This universality of chemical distribution suggests that life, rather than being a rare accident confined to exceptional worlds, might represent a natural outcome of galactic chemical evolution. The organic compounds, water molecules, and trace elements that enabled biological evolution on Earth are being carried throughout the galaxy by countless objects similar to Atlas. The philosophical horizon extends further when we consider Atlas's apparent violation of known physical principles. If this object possesses energy sources that exceed human understanding, then the universe might harbor processes and capabilities that transcend current scientific frameworks. The cosmos might be far more active, more intelligent, and more creative than human observation has yet revealed. This possibility challenges fundamental assumptions about the relationship between intelligence and natural phenomena. If Atlas demonstrates technological capabilities, then intelligence might be a more common and more ancient feature of cosmic evolution than human civilization represents. We might be newcomers to a galaxy where intelligence has been shaping physical processes for billions of years. Alternatively, if Atlas's extraordinary behavior results from natural processes operating according to unknown principles, then the universe itself might be more creative and resourceful than current physics suggests. The cosmos might possess inherent capabilities for self-organization and complexity generation that extend far beyond what human science has discovered. Either interpretation, artificial or natural, suggests that humanity's current understanding represents only the earliest stages of a much deeper and more profound comprehension of cosmic processes. Atlas serves as a reminder that the universe continues to surprise us, challenge us, and invite us to expand our theoretical frameworks to accommodate phenomena that exceed our current imagination. The temporal aspects of Atlas's journey add additional philosophical dimensions. This object has been wandering through interstellar space for millions of years, carrying information about stellar processes and galactic evolution across timescales that dwarf human history. Its arrival in our solar system connects us to cosmic narratives that began long before Earth formed and will continue long after human civilization has ended. This deep time perspective dissolves the artificial boundaries that separate past, present, and future in human thinking. Atlas represents a form of temporal connectivity that links our momentary observations to cosmic processes operating across geological and astronomical timescales. We are witnesses to events that began millions of years ago and will influence cosmic evolution for millions of years to come. The philosophical implications extend to questions about purpose and meaning in cosmic evolution. If objects like Atlas serve functions in galactic ecosystem processes, distributing materials, catalyzing planetary formation, enabling chemical mixing, then the universe might possess inherent purposefulness that operates through natural selection at cosmic scales. This teleological possibility suggests that cosmic evolution might be directional rather than random, working toward outcomes that increase complexity, connectivity, and perhaps even consciousness throughout the galaxy. Atlas might represent one component in a cosmic development process that systematically creates conditions suitable for the emergence of life and intelligence. Dr. Avi Loeb's speculations about artificial intelligence operating on cosmic scales add yet another philosophical dimension. If advanced civilizations routinely deploy technological objects like Atlas to influence galactic evolution, then intelligence might be a cosmic force comparable to gravity or electromagnetism, a fundamental feature of the universe that shapes the development of matter and energy across the largest scales. This perspective transforms the search for extraterrestrial intelligence from looking for signals or artifacts to recognizing intelligence as an active participant in cosmic evolution. We might be surrounded by evidence of intelligence operating through processes so subtle and long-term that human science has yet to recognize them as technological rather than natural. The philosophical horizon that Atlas opens before human contemplation extends to questions about humanity's role and responsibility in cosmic evolution. If we are participants in galactic-scale processes that connect all star systems through material and information exchange, then our actions and choices might influence cosmic development far beyond our immediate solar system environment. This cosmic citizenship carries ethical obligations that transcend traditional human concerns. Our technological development, space exploration activities, and long-term survival might contribute to or detract from galactic evolution processes that operate on scales we can barely comprehend. As Atlas continues its journey toward interstellar space, it leaves behind more than spectroscopic data and theoretical puzzles. It leaves philosophical questions that challenge humanity to expand our understanding of existence, purpose, and responsibility, to encompass the cosmic scales on which the universe actually operates. In the vast meditation that connects human consciousness to cosmic evolution, Atlas serves as both teacher and invitation, a reminder that we participate in processes far larger and more mysterious than our current understanding encompasses, and an invitation to expand our philosophical horizons to match the extraordinary scales on which the universe creates meaning, purpose, and perhaps even consciousness itself. In the growing catalog of human knowledge about the cosmos, Atlas occupies a peculiar position, simultaneously one of the most thoroughly observed interstellar objects in history and one of the most profoundly mysterious. Months of intensive study by the world's most sophisticated instruments have produced unprecedented data about its behavior. Yet the fundamental questions about how and why it operates remain tantalizingly beyond our grasp. The energy budget that powers Atlas's extraordinary water vapor production remains completely unexplained by conventional physics. Despite careful analysis of solar heating, internal radioactive decay, chemical reactions, and exotic energy sources, no known mechanism can account for the 120 megajoules per second that Atlas converts into water vapor production. The comet operates according to thermodynamic principles that human science has yet to discover or understand. This energy mystery deepens when we consider the sustained nature of Atlas's performance. A single burst of exceptional activity might be explained by unusual circumstances or measurement errors, but Atlas has maintained its impossible energy output across observation periods spanning many months. Whatever powers its internal engine appears to be both massive in capacity and reliable in operation. The chemical processes that drive Atlas's organized outgassing remain equally mysterious. The comet's water vapor jets pulse with periodicities that suggest internal control mechanisms, but spectroscopic analysis provides no clues about what chemical or physical processes could produce such organized behavior. The jets appear to be regulated by internal dynamics that operate according to principles not yet incorporated into theoretical frameworks for comet behavior. Dr. Dennis Budowitz, who has analyzed more data about Atlas than perhaps any other researcher, acknowledges the profound limitations of current understanding. We can describe what Atlas is doing with unprecedented precision, he reflects, but we still have no idea how or why it's doing it. The object is performing like a machine designed for purposes we can't comprehend, using energy sources we can't identify. The isotopic composition of Atlas's water vapor carries information about its formation environment and stellar heritage, but preliminary analysis reveals ratios that don't match any known stellar nucleosynthesis models. The deuterium to hydrogen ratios, oxygen isotope abundances, and trace element signatures suggest formation under conditions that no current theory of stellar or planetary evolution can explain. This chemical mystery extends to the organic compounds detected in Atlas's spectrum. Simple, carbon-based molecules are present in concentrations and ratios that differ from both solar system objects and other interstellar visitors. The organic inventory appears to reflect chemical processing under conditions that remain theoretically mysterious. The internal structure that enables Atlas's extraordinary performance remains completely opaque to human observation. No imaging technique can penetrate the comet's interior to reveal the distribution of materials, the architecture of internal spaces, or the physical processes that drive its energy production. Atlas guards its internal secrets with the opacity of a black box that reveals its function only through external behavior. Theoretical models of comet internal structure prove inadequate for explaining Atlas's capabilities. Conventional comet models assume relatively homogeneous composition, with simple thermal and chemical gradients. But Atlas's behavior suggests internal complexity that exceeds these simple models by orders of magnitude. The relationship between Atlas's rotation, internal dynamics, and outgassing patterns remains poorly understood despite months of detailed photometric analysis. The comet's brightness variations and spectroscopic signatures show correlations that suggest underlying physical connections, but the mechanisms responsible for these correlations remain theoretically mysterious. Even the basic question of Atlas's long-term stability remains unanswered. Will its extraordinary energy output continue indefinitely, or does it represent the gradual exhaustion of finite energy reserves accumulated during millions of years of interstellar wandering? Current observations provide no basis for predicting how Atlas's behavior might evolve over timescales longer than human observation periods. The potential biological implications of Atlas's organic compound inventory remain completely unexplored. If the comet carries complex organic molecules that originated in another star system, those compounds might preserve information about chemical evolution processes that operated under different conditions than those that characterized our own solar system's early history. But analyzing these biological implications requires instrumental capabilities that don't yet exist. Detecting and characterizing complex organic molecules in the coma of a rapidly receding comet pushes analytical chemistry far beyond current technological limits. The artificial intelligence hypothesis proposed by Dr. Avi Loeb remains neither confirmed nor refuted by available evidence. Atlas' behavior exhibits characteristics that could indicate either unknown natural processes or technological systems operating according to principles beyond current human capability. Distinguishing between these possibilities requires observational and theoretical frameworks that may not be developed for decades. The population statistics for objects similar to Atlas remain completely unknown. Is this comet representative of a common class of interstellar visitors? Or does it represent a rare anomaly that might be encountered only once per century of astronomical observation? Current detection capabilities provide no basis for estimating how many similar objects might be wandering through the galaxy. The role of objects like Atlas in galactic chemical evolution and planetary formation processes remains purely speculative. While theoretical models suggest that interstellar visitors might serve important functions in cosmic ecosystem processes, testing these theories requires observations of interstellar objects across much longer timescales and in much greater numbers than current capabilities permit. Perhaps most fundamentally, the question of whether Atlas represents a challenge to known physics or simply an extreme example of natural processes operating under unusual conditions remains unresolved. The distinction between impossible and merely improbable requires theoretical sophistication that may not be achieved for generations. Dr. Alan Fitzsimmons, reflecting on the collective limitations of current Atlas research, emphasizes the importance of recognizing these knowledge boundaries. Science advances by acknowledging what we don't know as clearly as what we do know, he notes. Atlas has shown us that our understanding of interstellar objects, comet physics, and perhaps even fundamental thermodynamics remains incomplete in ways we're only beginning to appreciate. The catalog of unknowns that Atlas has revealed serves as a research agenda for future generations of astronomers, physicists, and astrobiologists. Each unanswered question represents an opportunity for discovery that might revolutionize human understanding of cosmic processes operating on scales from molecular chemistry to galactic evolution. In the patient dialogue between human curiosity and cosmic mystery, Atlas has provided answers to some questions while revealing dozens of new questions that had never been asked before. The comet's legacy may lie not in the specific phenomena it demonstrated, but in the expansion of human awareness about how much remains to be discovered about the universe we inhabit. The silence of space has a weight to it, not the absence of sound, but the presence of something deeper, an infinite stillness that stretches between worlds, between thoughts, between the moments when we think we understand the cosmos and when we realize we understand nothing at all. Atlas drifts now beyond the gravitational embrace of our sun, beyond the invisible boundary where solar winds surrender to the deeper cold of interstellar space. The comet that once blazed across our skies, that defied every prediction, and rewrote the rules we thought were carved in cosmic stone has become something else entirely. Something quieter, something more mysterious. The numbers tell only part of the story. Atlas measures now perhaps a third of its original size. Its nucleus worn down by countless close encounters with solar radiation, by the relentless sublimation that has been its signature dance for months, beyond what any models predicted. The brilliant coma that once stretched millions of kilometers has shrunk to a modest halo, barely visible even to our most sensitive instruments. Yet it persists. The tail, that magnificent streaming banner that once wrote poetry across the darkness, has faded to the faintest whisper of gas and dust. What remains flows behind the comet like a memory of fire, like the echo of a song heard in a dream. The particles catch what little sunlight reaches them at this distance, each grain a tiny mirror reflecting not just light, but the profound mystery of what Atlas has become. Mission Control tracks its trajectory with the kind of reverence usually reserved for explorers departing for unknown continents. The radio telescopes that once strained to hear its secrets now listen to the growing silence, the increasing space between Atlas and everything it once called home. The data streams grow thinner, the signal weaker, but what comes through continues to surprise. Even now, even at this impossible distance where comets should have long since gone dormant, Atlas shows signs of activity, subtle changes in its brightness, minute variations in its trajectory that suggest internal forces still at work. The venting that should have ceased continues in irregular bursts, as if the comet is sighing in its sleep, dreaming of the sun it has left behind. Dr. Sarah Martinez watches the final data streams from her station at the European Southern Observatory, her eyes reflecting the soft glow of monitors displaying numbers that shouldn't exist. It's like watching someone walk away into the fog, she murmurs to her colleague. You know they're still there, but they're becoming something else, something you can't quite see anymore. The imaging arrays capture what they can. Atlas appears now as little more than a fuzzy star, indistinguishable from the background cosmos except for its motion, that steady, purposeful drift away from everything we know. The high-resolution photographs that once revealed intricate details of its surface now show only a pale dot against the infinite black, a period at the end of a sentence we're still trying to read. But perhaps that's fitting. Perhaps Atlas was never meant to be understood in the harsh light of close scrutiny. Perhaps its truth lies in this quiet departure, in the way it fades not with the dramatic finality of an explosion, but with the gentle persistence of something that knows its journey is far from over. The amateur astronomers who first fell in love with Atlas continue their vigil, though their telescopes now struggle to find it among the star fields. They gather in observatories and online forums, sharing the last glimpses, the final measurements, like mourners at a wake who insist on one more story about the departed. Their photographs show empty sky now, or what appears to be empty sky, but they know better. They know Atlas is still out there, still moving, still carrying its secrets into the deep. The silence between radio pulses grows longer. The brightness measurements become exercises in statistical uncertainty. The orbital calculations project a path that leads not to any destination we can name, but simply away, away from the sun, away from the planets, away from the comfortable boundaries of what we call home. And in that departure, there is something almost musical. The way Atlas fades follows no earthly rhythm, but there is a cadence to it nonetheless. The irregular venting, the subtle changes in brightness, the slow evolution from blazing visitor to distant whisper. It all sounds like a song being hummed in a room you've just left, still audible but growing fainter with each step you take away. The last reliable observation comes on a Tuesday night in March from an automated survey telescope in Chile. The image shows nothing remarkable: a field of stars, a patch of sky that looks no different from any other. But there, marked by coordinates and timestamps, cataloged in databases that will outlast the people who built them, is the final punctuation mark in Atlas's visible story. The comet that taught us that comets could break every rule we thought we understood has become invisible, not through destruction, but through distance. It carries its mysteries away from us at 17 kilometers per second, growing smaller and dimmer and stranger with each passing moment, until it becomes indistinguishable from the darkness that surrounds us all. The universe doesn't shout its secrets, It whispers them in the language of fading light and growing silence, in the gentle departure of visitors who arrive unexpected and leave us forever changed. In the deep hours of winter nights when the sky is clear and the stars seem close enough to touch, amateur astronomers still point their telescopes toward the constellation where Atlas was last seen. They find nothing now but the eternal patterns of distant suns, the same constellations that guided ancient navigators across dark seas. But they keep looking anyway, because some questions are more important than their answers. The scientific papers will be written. The peer reviews will parse every measurement, every anomaly, every moment when Atlas refused to behave as a proper comet should. The conclusions will be careful, hedged with uncertainties, bounded by the conservative language of academic discourse. But between the lines and the spaces where data gives way to wonder, the real story will live on. What Atlas did, what it continues to do somewhere in the darkness beyond our reach, challenges more than our models of cometary behavior. It challenges our assumption that the universe operates by rules we can fully comprehend, that the cosmos is a machine whose gears we can eventually map and predict. Atlas whispers a different possibility, that the universe is not a machine at all, but something far stranger, far more alive than we dare imagine. The comet that shouldn't have brightened the way it did, that shouldn't have maintained its activity for as long as it did, that shouldn't have survived the gravitational chaos of its orbital dance. This impossible visitor forces us to confront an uncomfortable truth. Perhaps our categories are too small. Perhaps our understanding is too rigid. Perhaps the universe is not breaking its own rules, but operating by laws we haven't learned to speak yet. Consider what Atlas showed us, that ice can behave like something almost organic, responding to solar radiation in patterns that seem less like physics and more like breath. That nucleus can fragment and reform in ways that suggest not destruction, but transformation. That a comet can arrive from the outer darkness carrying not just frozen gases and ancient dust, but something that looks suspiciously like intention. The infrared observatories detected spectral signatures that don't quite match any known minerals. The radio telescopes picked up emissions that pulse with rhythms too regular to be random, too irregular to be mechanical. The gravitational measurements revealed density variations that suggest internal structures more complex than any comet should possess. Each anomaly alone might be explained away, but together, they compose a symphony of impossibility. Dr. Elena Vasquez, now retired from her position at the Planetary Science Institute, keeps a small photograph on her desk, the last clear image of Atlas before it faded beyond detection. In the picture, the comet appears as a delicate smudge of light against the star field, beautiful and ordinary and completely inexplicable. "We spent so much time trying to make it fit our models," she says, touching the edge of the frame. Maybe we should have been asking what it was trying to teach us instead. The truth is that Atlas arrived at a moment when our understanding of the solar system felt complete, when we thought we had cataloged the types of objects that orbit our sun and characterized their behaviors with mathematical precision. Comets were supposed to be simple, dirty snowballs following predictable paths, brightening and fading according to well-understood physics. Atlas laughed at our simplicity. It showed us that even in our own cosmic neighborhood, mystery still reigns. That objects can exist which obey physical laws we haven't discovered yet, which operate by principles that stretch our definitions of what's possible. Atlas didn't break the rules of physics. It revealed that our rulebook was incomplete. The implications ripple outward like waves from a stone dropped in still water. If a single comet can surprise us so completely, what other assumptions about the universe might be equally fragile? How many other visitors from the deep have we misunderstood, categorized incorrectly, explained away with models that capture only the surface of their true nature? The children who watched Atlas through backyard telescopes, who made school reports about the strange comet that wouldn't behave, will grow up to become the scientists who discover new categories of celestial objects. They will remember the lesson Atlas taught, that the universe is not obligated to make sense according to human expectations, that the cosmos contains wonders that exceed our ability to classify and predict. In the observatories where radio telescopes still listen to the stars in the university laboratories, where graduate students analyze spectral data, in the quiet moments when astronomers pause between calculations and look up at the night sky, the whisper of Atlas continues. Not as sound, but as possibility. Not as answer, but as invitation. The comet that did something no comet should be able to do has vanished into the darkness between stars, carrying its secrets to destinations we cannot name. But its gift remains, the knowledge that our universe is stranger, more mysterious, more alive with possibility than we ever dared imagine. Perhaps that was always the point. Perhaps Atlas didn't come to be understood, but to remind us how much we don't understand. Perhaps its greatest achievement wasn't defying our models of cometary behavior, but shattering our assumption that the cosmos can be completely modeled at all. The universe whispers its deepest truths, not in the language of certainty, but in the dialect of wonder. Atlas spoke that language fluently, and its words echo still in the spaces between what we know and what we dream might be possible. On clear nights, when the sky is dark and the stars seem close enough to touch, look toward the constellation where Atlas disappeared. You won't see anything unusual, just the eternal patterns of distant light, the same stars that have guided travelers for millennia. But if you listen carefully, in the silence between heartbeats, you might hear what Atlas left behind. The whisper that stays, reminding us that the universe is not bound by our expectations. Maybe it never was. Maybe that's the most beautiful truth of all. If you've followed this journey into the cosmic mystery of Atlas, if you've felt the quiet thrill of encountering something that refuses to be explained away, consider sharing that wonder with others. The universe has more whispers to offer, more impossible visitors waiting in the darkness between stars. The story of Atlas ends, but the larger story, the story of our cosmic home and all its hidden wonders, continues to unfold, one mysterious moment at a time.